కంపడదు
వినపడుతుంది.
within them.
ఆడియో కూడా వస్తుంది. Good morning, sir.
Hello, good morning. Good morning, sir. It's
Good.
10:30, right?
Yeah.
So, shall I start, sir? Jeevan, sir. I'm ready. Can you hear me?
Yes, ma'am.
Okay. Okay. Thank you.
Madam, please start. Madam.
Sir, start చేయమంటారు.
చేయండి
కన్వీనర్ అండ్ వైస్ ప్రిన్సిపల్ అని చెప్పండి మేడం.
కన్వీనర్ అండ్ వైస్
ప్రిన్సిపల్ అని చెప్పండి. రతన్ సార్ కొంచెం
సార్ బిజీలో ఉన్నారు.
ఓకే, మీరైతే రెడీ?
కన్వీనర్ అండ్ వైస్ ప్రిన్సిపల్
కన్వీనర్ అండ్ వైస్ ప్రిన్సిపల్ అని చెప్పండి.
ఓకే
ఓకే
ఓకే.
Hola.
Please start.
Okay. Hola. Good morning, everyone. My name is Anjali. IQSC coordinator of this 19 established SR&BGNR Government Arts and Science Autonomous College, Khammam. I want to tell you just 3 things about our college. It's a reputed and well-known college in Khammam district, and it stands in the 5th place of best colleges among degree colleges in Telangana state. And I'm very happy to announce that we are concentrating on outcome-based learning, which is very essential to the students. So now coming to the point, our the dignitaries gathered here to attend this one-day international webinar on recent trends in solar power technologies and elementary particles conducted by our Department of Physics. Now, welcome again. Now let us have the pleasure of listening to the welcome address of the webinar convener, Sri T. Jeevan Kumar, HOD, Department of Physics, and Vice Principal of our college. And actually, this is not the right platform, but I want to tell you one thing: he's a good social worker and karate master too. So I welcome Jeevan sir to give his welcome address. Sir, we would love to hear from you. Welcome, Jeevan sir.
Thank you, madam. Thank you very much. Good morning to everybody. Me, Jeevan Kumar Totapalli, working as a physics teacher at SR&BGNR Government Arts and Science College, Khammam. I am very happy to meet you on this international webinar that we are conducting with 2 internationally acclaimed speakers of eminency, Dr. Bobbili Prabhakar Rao, sir, Senior Research Fellow, London South Bank University, UK, and Dr. Jammu Ravi, sir, Scientist E. Izikar Kalpakam, Tamil Nadu, India. From the blessings of our dynamic commissioner, Sri Naveen Mittal, sir, and the endless support of our beloved principal, KSS Rathamsad, sir. Physics is the subject which transforms the society from ancient to modern. The whole university is filled and existing with energy. Only from the a very minute particles, means elementary particles, to huge bodies like stars. The key to open a comfortable modern life will be the proper utilization of the renewable energies. In that aspect, these checks are arranged. Please go through. These talks are arranged. Please go through. Thank you, one and all. Thank you very much. And ma'am, I'm handing over to the madam, Anjani madam.
Okay, thank you, sir. Thank you. Your brief note on this occasion. And I think our principal, sir, is not available, but I want to tell you something about him. Who's the creator of a friendly and family atmosphere in our college, and very humble, and he has down to earth attitude. If he is here, he'll deliver his speech. Otherwise, I'll move to the next speaker. Sir, I think sir is not here, right?
Ma'am, madam.
Principal sir is not here now.
Yeah, madam.
Okay, sir. I'll invite Dr. Balabhaskar, sir. Is he available, sir, now? Dr. Balabhaskar. I'll invite him. So I feel very happy to take this opportunity to invite our guest of the day, Dr. P. Balabhaskar, AGO CC, Telangana, who has more than 25 years of experience as an academician, and who received gold medals in Usmania University while he was studying physics, and participated in many workshops, seminars, conferences. Not only participated, he has conducted so many seminars, webinars, and conferences too. And he supports all the degree colleges because he came from the colleges. He understands the problems and issues and needs of the colleges. So he's always ready to help and give his supporting hand to the degree colleges because he is from the degree college. So I welcome Dr. Balabhaskar Garu to give his valuable message on this occasion. Dr. Balabhaskar Garu, welcome, sir.
వస్తున్నారు మరి
So, sir, shall I move? Shall I invite the next speaker, sir?
Please, madam. If
Okay.
sir joins,
Yes, actually, there are two reasons. They are busy and due to some technical reasons, they are not available, and sorry for the inconvenience. Right, I'm moving to the next part of the session. Now, with so much enthusiasm, I invite Dr. BSR Rajendra Singh, RJD, CC, Telangana. He is the principal of GDC Khairatabad, who has so much experience in research, more than 10 years experience in research, and around 17 books he has published on his name, and so many research papers, more than 25, I think, and so many articles in different journals, reputed journals, and he presented so many papers in seminars, and he conducted radio talks and Mana TV programs, and he has experience in social service in more than 20 years. With this introduction, I invite and I request to give his message on this occasion, Dr. DSR Rajendra Singh. Welcome, sir. Jeevan sir, I think he is also not here, right? So it is our honor to honor our CCE people. That's why we included them. Even if they are not here, we have to honor their work contribution to our colleges. That's why we are saying all these things. And now, actually, we requested our commissioner sir to give keynote address, but as you people know, he's always busy with other work. So, but I want to tell a few things about our commissioner sir, Naveen Mittal IAS. He is a Delhi IITN turned into an IAS. Did so many adventurous things in his career as a collector and director of ITDA. Operation Kolleru, as you people, many people who follows TV, they definitely know that he did Kolleru operation and so many rescue things. And GHMC commissioner, he did so many things. And I want to tell you one thing about the higher education. A commissioner of colleges education, he has done so many things. He's putting endless efforts in degree colleges to improve their standards. Usually people think that government colleges not capable or not efficient, but he's trying to improve the standards and taking these colleges to the heights of international standards. For that, we are very happy and thankful for him. Uh, so, Jeevan sir, can we move to the technical session if the resource persons are available?
Yeah, madam, resource persons are available, but Balavaskar sir is coming to talk. So, okay,
Sir,
madam.
Sir has joined, I think.
Ravi sir.
I can't see the names, sir. That's why I don't know whether they have joined or not. So just check the participants list and tell me.
So, good morning, Andy.
Good morning, sir. Good morning. Thank you, sir.
Good morning. Good morning.
Welcome, sir.
Thank you, ma. Thank you. Thank you. Thank you. I think a series of webinars are being organized by the Kamam Degree College. Very happy. I think for me this is the fourth invitation, and the invitation now it is very special for me because it is our department, our physics department is conducting this particular program. For that I am very happy. The topic that what they have chosen is the solar power. Solar power technologies and elementary particles. I think it is one of the very interesting and a very important, very useful topic that they have chosen. The students of physics department can make use of this particular webinar because they even study about the conventional sources of energy. This solar power is one such energy. It is very useful nowadays. The solar power is being widely using not only in the industrial this one and also for the home or domestic purpose also. So still coming to our research aspects, I think solar power is panels are being there, but even there are so many issues that are to be addressed. Still, the research, there is no research in the solar technology. So this is one thing that has to be addressed. Definitely new materials have to come in. What are the issues on the solar power panels? Those things have to be addressed. So for this, I am very happy. And SR college for being organizing such programs. And not only that, we also thank the resource persons who are there for today. because they are spending their valuable time with us. So we must also thank them, and especially to the principal and the organizers. Thank you very much. And మెయిన్ గా ఉన్నటువంటిది చెప్పదలుచుకున్నది ఏమిటి అంటే, బికాజ్ ఇట్ ఈస్ ఫిజిక్స్ రిలేటెడ్ టాపిక్ కాబట్టి డెఫినెట్ గా ప్రాక్టికల్ నాలెడ్జ్ అనేటువంటిది మనం స్టూడెంట్స్ ఇవ్వాల్సిన అవసరం ఎంతైనా ఉంది. బట్ నవడేస్ మరి థియరిటికల్ నాలెడ్జ్ అనేటువంటిది క్లాస్ రూమ్ టీచింగ్ తోటి బాగా ఇస్తున్నాం మనం. బట్ దెర్ ఈస్ అన్ ఇష్యూ with the practical knowledge. In the earlier days, we used to have so many number of practicals we used to do in the laboratories also. But ఇప్పుడు ఈ కోవిడ్ సిచ్యువేషన్ వచ్చేసింది, దీంతో మనకి ఏమవుతుంది అంటే ఫిజికల్ గా ప్రాక్టికల్స్ మీద మనం కాన్సన్ట్రేట్ చేయడం అనేటువంటి తగ్గిపోతుంది. మరి ఇటువంటి సిచ్యువేషన్ లో దేర్ ఆర్ సో మెనీ ఏమంటాం మనం వర్చువల్ ల్యాబ్స్ కూడా మనకు అవైలబుల్ గా ఉన్నాయి. కాబట్టి I appeal to all the physics teachers, not only physics teachers, to all the science lecturers to make use of virtual laboratories. అది పిల్లలకు మరి ప్రాక్టికల్ ఇన్ఫర్మేషన్ మనం ఎంత ఇవ్వగలిగితే డెఫినెట్ గా వారిలో ఉన్నటువంటి యొక్క రీసెర్చ్ మీద ఉన్నటువంటి ఈ జిజ్ఞాస కానీ తృష్ణ కానీ ఇంకా పెరిగే అవకాశాలు ఎక్కువగా ఉంటాయి. కాబట్టి I appeal to all the science lecturers of Telangana state, please try to give more knowledge in the practical domain, so that the students can make utilize and they create some interest over the subject also. So this is one thing. And the solar panels ki sambandhinchi, solar energy ki sambandhinchi solid state physics లో ఈ ఫైనల్ ఇయర్ స్టూడెంట్స్ తప్పకుండా చదువుతారు. మరి వారికి ఈ సెమినార్, ఈ వెబినార్ డెఫినెట్ గా ఉపయోగపడుతుందని నేను అనుకుంటున్నాను. ఖచ్చితంగా ఈ యొక్క ఏరియాలో ఉన్నటువంటి రీసెర్చ్ లో ఇంకా అంటే సోలార్ ప్యానల్స్ మనం ఉపయోగిస్తున్నప్పటికీ ఇంకా మనకు బ్రేక్ త్రూ మెటీరియల్స్ అనేటువంటివి ఇంకా రావాలి. అవి వచ్చినప్పుడు తక్కువ ఏరియా ఉన్నటువంటి ప్యానెల్ తోటి ఎక్కువ పవర్ ని జనరేట్ చేయాల్సినటువంటి రోజులు రాబోయే రోజుల్లో ఉన్నాయి. కాబట్టి ఈవెన్ సోలార్ ఎనర్జీ కెపాసిటీ తక్కువ ఉన్నప్పటికీ, ఎనర్జీ రేడియేషన్ తక్కువ ఉన్నప్పటికీ మోర్ సోలార్ ఎనర్జీ కన్వర్ట్ 100% ఎఫిషియెంట్ ఉన్నటువంటి ప్యానల్స్ ని ప్రొడ్యూస్ చేసేటువంటి టెక్నాలజీ మనకు రావాలి. కాబట్టి ఆల్ దీస్ థింగ్స్ హావ్ టు బి అడ్రెస్డ్. And I wish once again the organizers and especially the physics department of Common College all the best. And I also thank the principal and the organizers of this webinar for giving me this opportunity to address today. I thank you one and all. Thank you very much.
Okay, thank you very much, sir. Okay, actually, we got an opportunity to hear a message from a physics gold medalist in this physics webinar. Actually, I want to tell you your subject. I said you want a gold medal, but I forgot to tell that it is in physics. Okay, kind support and words of wisdom, and it will be a great pleasure for us to listen to you again in our future events. And
Thank you.
To attend our events.
Thank you, madam. Thank you.
So now I welcome and thank our real heroes of this webinar, the esteemed resource persons. One is Dr. Bobili Prabhakar Rao Garu, Senior Research Fellow, London South Bank University, United Kingdom. Another one is Dr. Jemmu Ravi, Scientist, IGCAR, Kalpakam, Tamil Nadu, India. I welcome these two esteemed resource persons and thank them. Now I request our convener of this webinar, T. Jeevan Kumar sir, to conduct this technical session. Over to Jeevan Kumar sir.
Thank you, madam. Thank you very much. So I am requesting our colleague and good research scholar, Ravi Kumar sir, to invite and to introduce Dr. Bobbili Prabhakar Rao sir, an esteemed speaker to this session.
Sir, thank you, sir. Good morning to one and all. It's very happy to see overwhelming response of the participants. Almost 212 members have joined so far. And now, on this occasion, I would like to speak few words about. I would like to speak few words about Dr. Prabhakar Rao Bobbili. Sir is basically from Vijayawada. He's an eminent scholar, and his basic area of research is in heat exchangers, heat transfer, and process equipment. In addition to that, he has also worked on integration of solar PV and thermal systems, including concentrated solar PV thin films, thermoelectric and thermal energy storage systems, boiling and condensation on micro nano surfaces, and he has produced so many papers over the 15-20 years, and most of the papers are published in reputed international journals, and so many of his papers, so many papers were referenced by other scholars, referred by so many other scholars, and at this juncture, at present he is working in London South Bank University, and further about his career, few more things about he is a founder and CEO of M Delta his systems, London, UK, and he is also director of MCS Electronics Private Limited, Bangalore, India, and his PhD area is in thermal engineering at IIT Madras, Chennai, and his master's in
ಕೋಪಮತ್ತೆ
sir, Prabhakar sir. Sir, Dr. Prabhakar Rao Bobbili garu, good morning sir. Are you able to hear me, sir? Yes, sir. Sir, we are very much thankful to you for accepting our invitation and accepting to speak to our students about your share your knowledge and expertise in your area of research, sir. And on this occasion, we invite you to address our students.
Thank you, Ravikumar sir.
Yes,
Can you please allow me to share my content?
sure, sir. Sure, sir.
Yeah, thank you so much, Jeevan sir and Ravikumar sir, and other delegates.
Yes, sir.
Sir, now you can share your slides.
Yeah, thank you. Am I able to
Yes, sir. Yes, sir.
yeah,
Yes, sir.
okay.
Yes, sir. Yes, sir.
Yeah, thank you very much. The Khammam Gout College, is a BGNR college, and management and the principal and vice principal and the convener.
Sir, it is not audible, sir.
Now?
Yes,
Hello?
sir.
Yes, sir,
Yeah?
please.
It's okay, sir. Sir, again your audio has gone, sir. Prabhakar sir, please check your.
Sir, your audio is not clear.
Hello?
Yeah, now it's okay, sir.
Yeah. Now it's okay?
Yes, sir. Now it's okay.
Yeah. Thank you. Thank you so much. Thank you. I don't know why it's going regularly. Hello?
Sir, I think you are using two devices, one for
Yeah, I'm
video,
using
one for.
you can because my computer microphone is not working. I'm using my phone one. So please allow me to speak on the other one, like the
Okay,
Prabhakar.
sure.
Yeah,
Thank you.
yeah.
Please go ahead, sir.
Yeah. Thank you so much. So today I would like to present on the recent trends or the technologies, basically solar power technologies. So here actually before, I thought it is very useful for our people because a lot of renewable energy technology, and also the conventional, non-conventional. For example, if you come to that one, it's a non-conventional resource, and also it is very abundantly available in the universe. So that's why we want to tap as much as possible. So that's why because I'm working in this area for last 10 years. I will. Yeah. So my background, just thank you very much, Jeevan and the Ravi Kumar gave me small brief about me, but I would like to give you my background. So who am I? So I come from, as I said, Vijayawada, but I come from the nearby, just border to the Khammam district. It's called Vatsavai Mandal. It's a small village called Khammampadu. And then after that, I studied mostly my childhood from Vatsavai. And then I studied my 10th class in Nandigama. And then I went to Vijayawada, Pune Lakshmi Engineering College. And then after that, then I did through GATE exam, and then I went to Pondicherry Engineering College, where I studied energy technology. And then after that, I was again back to the Khammam. Actually, I worked in Wazir Sultan College. In Wazir Sultan College, I worked as a lecturer. So in 1988, 88 some time in that time. So I worked for 4 months only. Then I went to again Pune Lakshmi Engineering College. Again, I worked as a lecturer. And then after that, I went to PhD program in IIT Madras. So then there actually I did my PhD in plate heat exchanger, basically heat transfer. You might have seen, heat transfer, thermal engineering, etc. So here actually I worked with Professor Sarit Kumar Das. He is present currently director IIT Ropar. So Professor Sarit Kumar Das, he really gave me insight to the research, and he very helped me. And he was a very friendly person actually. So though he's from West Bengal, so very friendly and humble person. And then I went to, after my PhD program, I went to Sweden, where I worked as a Lund University. So Professor Bengtsson worked as a research associate, postdoctoral research assistant, or something, what do you call. And then I went to UK, United Kingdom, especially in Scotland, where Harriet University. There I worked with Professor Peter Q. He's an expert in the boiling, where I have a chance to work in a micro channels. The channels are size is about 1 millimeter diameter. And then after that, got a chance to work on the solar systems, nanotechnology, nanomaterials, thin films. So more related to physics, because the engineering also is applied physics. So therefore, whatever, even in the Western countries, most of the physics department people are working is like engineering section. So we don't differentiate engineering or physics, applied physics, whatever it may be. So therefore, this is this is my brief, my profile. Then after that, getting experience, practical experimental journal publications, etc. Then I started a company. It's called M Delta. Also, I've been involved in the Bangalore company as also invested as a director. Recently, actually, I resigned actually from there. And then, so solar energy, we have abundant energy available. Sun, very bright sun we have in India especially. But we here in UK we have very less sun, but still we are using a lot than India. And my content, what I'm planning to do, actually, I want to give a overall picture of, because even the common student to understand these solar power technologies, solar energy technologies, we can say that way. So, and then also in that, I want to see, I want to give small introduction, like a radiation, how the sun, from sun to the earth, and then how we want to capture this all energy, available energy. So I will give that information. And also I will give the comparison. What is the solar thermal? What is the solar PV? And also need, demand, what are the barriers between them? Also solar PV technologies, different technologies, what are they available? Whatever you are seeing on the rooftop, that is a silicon-based technology, but other than the other technologies, also I'll give you introduction for that one. But mostly I will concentrate on solar thermal because that is my expertise actually. So therefore, I will give you the most of the thermal technologies in the solar using the solar energy. Then for capturing the solar energy, there are solar thermal collectors are there. So then I will give you more information on this one, and also different applications like cooling, heating, refrigeration, power generation, etc. So yeah, this is the picture. This is the slide shows final this an energy demand globally. Global energy demand, how much is there? Hello.
Yes, sir.
Yes, sir, we getting your voice. No problem. You can carry on.
To the power of 18, you can say that, So this is the energy, total energy required, and then how much we have, so how much we can tap from the solar energy. So here actually this is the various technologies, solar energy technology. I want to give you a brief the various technologies using the solar energy technologies. So how the solar energy utilization, how we can utilize, what way. So there are direct conversion and indirect conversion as well. But I am not concentrating on the indirect conversion, and only I'm kind of concentrating on today in a talk direct conversion as well. In the direct conversion itself, we can classify it into two: one thermal, another one is photovoltaic. So in the for thermal, and again for thermal engineering, so it's like a heat and process heating, power generation, refrigeration, drying, etc. Today I will show you more information as well. Also, I will give you small introduction, small brief photovoltaic technology as well in the for few slides on that one, and power generation. So actually, what is the thermal, solar thermal? What are the main applications? What are, when you want to select a technology, which you want to, whether you want to install a PV panel or a solar thermal power generation. So what type of you want? What actually main application differences? So here is the one of the big challenges, price actually. So if you want to go to any project, for example, if you want to install any project, if suppose if you have an even commercial or a domestic applications, first we have to see our budget. So that's why the price is very important. That's why the major challenge is the price. That's why these thermal applications, the massive price reduction of the because from since 2005, it was the price was massively reduced, and although the prices for solar system did not significantly drop between 2000 and 2013, but PV panels, PV technology has 70% between since 2009 actually. So and also this challenge thermal system is therefore one hand reduce the price system, and also one other hand make the installation maintenance. So there are a lot of issues are there. I mean, we have to consider. So solar thermal technology is more space efficient. That means solar panel, it takes very large space is required for solar PV technology, whereas solar thermal technology, it requires only a small, because I will tell you why it's a small, less space is required for solar thermal technology. I'll show you there. So that's an advantage of solar thermal technology over the solar PV. Then solar thermal trends up to 70% more efficient, even if very efficient as well, because sun available only morning 6 to evening 6 in India, but other countries like UK, we see now we are time around 6 o'clock, but we are like a midnight kind of thing for us. So, and the technology itself a lot complex than PV. So less complex because the technology itself, I'll show you how that is technology difference from the PV, because producing a solar panel itself a lot of complexity involved. So solar thermal is a low grade energy, and also demand aside, because we mostly use the heat, especially Western countries, especially UK. We use more heat because we are cold countries, and also in India we use more cooling purpose actually. So therefore, even industries wise, we use more heat thermal energy, because steaming, the processing, drying, etc. So we need more thermal energy. Therefore, the industrial process accounts more 2/3 of total global industrial energy consumption, and half of the demand occurs at temperature below 400 degrees, because the temperature range is important, whether a low temperature, medium temperature range, or high temperature range. So more our applications are below 400 degrees. So, and approximately 40% of current industrial energy consumption is covered by natural gases. So approximately 40% of petroleum products are, according to this International Energy Agency, Renewable Energy Agency, according to that one. These are the data. In several industrial sectors such as food, wine, beverages, even for food, preparing a food, we use lot of heat, and also thermal energy we use. Even to prepare the wine in Western countries, and beverages, textile industry, even all the industry process, mostly process heat is involved. So there actually we need a lot of thermal energy. And most of them are below 250 degrees, around 60%. So then in Germany, for example, because I have got some Germany data here, you can see various sectors, transport sector, industry, services, transportation, etc. Next here this is the industrial in Germany, for example. So there are for 300 to 500 degrees, 4%, and the temperature range, different temperature range. But if you look at here, less than 100 degrees C, also greater than 500 degrees C is more 65% is there. We have to see how much energy. Because heat is thermal energy with the temperature range is very important when you're selecting the technology. So now I come to the solar power, solar energy. So I think you might have seen this is the picture. Is a hope you can recognize this picture, and this picture tells it's a fireball. The fire. Just even when you feel cold, also we fire it. So this fire, this is a thermal energy. This is the source of universe. Whole universe is involved on this one. So you can see how it is. And then if the earth had no atmosphere, what happens actually? Because if this is the way, there is no atmosphere, what happens actually? So all the, it's like a bug energy compound to the the earth and it will burn. Actually, it's like a missiles of fire. So now due to earth atmosphere, then actually we are getting only energy from the sun about an average on earth. That's called a solar constant. We are reaching about 1,360 watt per meter square. That means per unit area, per meter area square. Meter means 1 by 1 meter square. So we are getting the onto the surface of the earth. Even near the atmosphere, we are receiving about 1,360. And then from there are a lot of, because so much energy is available on the sun, but due to atmosphere is filtering. And then we're receiving only some part of countries we're receiving very small energy, and where other parts of energy. I'll tell you where the location which one is more receiving. So when sun's emitting the energy, then it receives on the solar panels. But these all solar panels, solar collectors, etc., we will see what happens there. This is what is the solar constant is, because sun. This is the way they calculate it, because of the sun diameter and then earth diameter. There is an angle. Then there is a solar constant is about here. You can see in the units. And these are the calculations have been made. So my average is about 1,360. So that means we can guarantee that much. And also, how do you know? Because globally, these variations are there in different locations. Say, if you are in Khammam, for example, how much your energy is receiving is different from the in Delhi. So even in London, different there. But this is the energy, solar energy available in the atmosphere. So nearby before reaching this. So we can calculate there is a n is the number of days in 365 days. So if you keep the n number value, you will get the global extraterrestrial radiation from the sun. So this is the calculations are there. You can estimate. You can estimate giving that one. And also if the theta, this azimuth angle, there is a azimuth angle is that actually tells on the Earth's location of your panel. Whether it's in Khammam, we will take the latitude and longitude angles. Once you put into the software, you will get the data, how much especially available in the Khammam area. So these are the, suppose if they are in the heat transfer, in a solar radiation or a radiation heat transfer, we will see this type of equations. If there is one is a source, one is a receiver, and you have different areas, 2 areas, and emitting, so you can calculate how much energy is receiving. And also this is this mapping. This is the map tells us how much actually energy is receiving onto our local areas, for example. Especially if you take in India here, a circle one, and then if you see the range in say yearly sum, so an average value in a year over of annually. So we are in this zone, something like 1,600 to 2,000 kilowatt hour per meter square. This is for overall per year annum per year. This much energy is available, but whether we can tap that much energy. How can we tap that one? So how much actually available? This energy, see, exa means so 10 to the power of 18, and see the amount of energy receiving by Earth surface per year. This much. You can see the numbers here. And then in 2013, the literature shows worldwide the primary energy consumption is about, out of this, only 550 exajoules worldwide. This is the worldwide energy consumption, 550 exajoules. And then, because if you consider only 6 hours for solar energy in deserts, the annual global energy requirement is we can meet 6 hours of solar energy at deserts can meet annual global energy requirement. And also solar energy technologies, various technologies. Now I will focus on the photovoltaic. That's a small brief I'll give you. And then here is various technologies. We can, whatever you're seeing in the solar rooftop or any solar field. So, but the panel, whatever the panel is, you can see different panels are there in this market actually. So, but in the research actually, in the research point of view, you can see there is a multi-junction solar cells and also single junction solar cells. So in single junction solar cells, the materials is mainly material actually. What we do here in our laboratories, we will deposit the materials. So whereas silicon, even thin film technology, because I work with the CIGS in the thin film technologies, CIGS, cadmium telluride. These technology I was working in the laboratory. I deposited. I even I developed. I was involved in developing a machine, CIGS machine in that CIGS system. Even I commissioned that one CIGS system. CIGS means copper, indium, gallium, and selenium. Selenium is a very toxic material, but it's a component. When it comes to the component, it's not a toxic actually. But if we take individually, selenium is very dangerous actually. But when you look into the component, but it's just not metal, just like a metal. So then another emerging technologies like a dye sensor solar cells. For example, dye sensor solar cells also dye. We use dyes, dye, whatever in color dyes. We extract it from the fruit, and that we use in the solar cells. I'll show you that also what type of this dye sensor solar. I work with the dye sensor solar cell as well. So, but the primary, whatever you're seeing on the rooftop, solar field, those are crystalline solar cells. That is a monocrystalline, polycrystalline kind of thing. Okay. So in India, we mostly using these silicon-based technologies basically. So here the main, so that's why we call it as a first generation solar cell. That is a silicon solar cell. That is a monocrystalline or polycrystalline. Then second generation solar cell. That's a thin film solar cells, CIGS, dye sensors. Then now recently we are concentrating on the perovskite because dye sensor is more related to dye sensor solar cell only because we are using dye when we, but there is a time limit, there's a temperature limit is there because the dye is a liquid, it will evaporate after keeping for some time. So that's why to avoid that one, then the latest technology is called the perovskite solar cells. So I'll show you how they do. Whatever you are seeing this in pictures here, these are the rooftop silicon-based solar cells. So monocrystalline means a pure silicon, whereas polycrystalline means is a different components, is less pure and in material wise. If you here the solar fields are there, so we can tap it, and these are the trends actually basically. So how the technology, various technology are using. So as the previous shown that this is the, because here you're unable to see properly. That's why I put all the information. But maximum efficiency, if you see the top of the trend line, so multi-junction solar cell, that actually we can tap the 43%, 47% we can achieve it. 47% achieve it. You can achieve the 40% with multi-junction solar cells. Whereas in coal-based power plants, the efficiency is about only 35 to 40 maximum. So therefore, we are almost reaching the near to the conventional sources like coal, the other sources. In India, we use more coal and hydraulic based systems. But now the government of India is encouraging to use solar energy. So they're encouraging subsidies, etc. So because it's easy to install, there's no less maintenance actually. It's a solar PV related technologies. So these are the various efficiencies, right side shows various efficiency of the various technologies. So many companies involved, so many people, different they're producing actually. So therefore, the now current status is about 47% we can achieve, but on the rooftop one, we are about 20% actually. What you are seeing, what if you buy, if you approach the any commercial vendor, they will say, oh this solar cell is about 20% on the paper, but on practically it would be like a 15% actually. So you can, that means 15% means, say for example in Khammam, if the solar energy receiving say for example 1500 watts per meter square, per meter square, you will receive the of that one as 15%. Okay, say if 1000 you are receiving, that means 15% means 150 watts per meter square. Per meter square, 1 meter by 1 meter. say meter square. If there's a panel is there, 1 meter by meter, you will receive the 150 watt. Say that one, if it's the 15%, then that's why the size of the solar panel is important here. That's why if you say 350 or 330 means the size of the panel is more. So that's why you can select what way you want. So if you have to see when you're buying the solar panel, you have to see the specific technical data sheet. Okay, how much, what is the modular efficiency, what is the cell efficiency? They'll give you both, but don't depending on cell efficiency. Cell efficiency based on the laboratory based. We have to see the module based one. So these are the dye sensor solar. See, this is the configuration, because what we do, we take the FTO glass. FTO means foreign doped glass, and then we put the one layer of the titanium oxide, and we'll put the dye onto that, soaked into the dye, and then we'll again cap it, and we'll make a seal it, and we make a holes, and then we fill the electrolyte, and then when you put into this exposed sunlight, it will produce the power. So this is the basically this is like a dye sensor solar cell. These type of solar cells even useful for the even curtains. We can make it even curtains. For example, in this window, when you are using curtains, we can make it. So even whatever the color you want, if it's more transparent or less transparent, you can choose the colors, size. So color and whatever you want. So these dye sensors, but these are very less efficiency. In my laboratory, I produce about only 6%. Okay, so this is the dye sensor solar cell, and this is the thin film solar cell. Like as I said, it's just on a sheet, like a metal sheet, or a plastic sheet. We can, or even tiles you can coat it. Even car dome, you can coat it. So these are the you can place on that one. This is the thin film. So you look at it, they're very flexible. These are sheets actually. These are the new technique. As I said, dye sensor solar cells is replacing with the perovskite, because there the dye is a liquid. Here in this perovskite, there is a perovskite material like a lead-based system that actually replacing with the dye that in the place, that one. So these are the PV technologies. And then if you look at here, even our cities, for example, our gardens, we can make solar panels like this. See, just like an umbrella, or tree shape or flower shape. You can make whatever shape you want. These are the solar panels, and you can capture the energy. So yeah, this is like a company called Smart Flower. The company name, they are actually producing this type of solar. It's a configuration, but cell is a silicon based or thin film based. But whichever way you want, you can mount it. So however you want. And also we are using these solar panels. We can use for the boat. This is a boat actually, basically the boat racing, etc. There we can use the solar panels, and no need fuel. Even for our fishers, we can use solar panels. No need diesel and etc. So you see here is another solar panel. The solar energy they are using in the cruise itself. So here we can make the main motto is here reducing the consumption of the fuel, the diesel or petrol or like conventional sources. We have to minimize that, because global warming, etc. I don't want to talk more about global warming. This is so here. And then I want to consider, after that, I want to consider thermal solar technologies here. Then thermal itself, we have to classify, because when you are selecting a technology, temperature range is very important. What people will ask the customer or a client saying that, yeah, I want to install, I want to use a solar power. Okay, what is your requirement? You ask you. Well, then based on that, we suggest you. Okay, I want thermal based technology. Then what temperature you want? Say 60. Say so. Depending on the temperature range, we will suggest. So different. For example, the process heat uses in industries 60 to 260 degrees. And whereas if you are able to produce the temperature like a steam or oil heating, we use oil heating for the this one. So water heating, drying food, cooking, distillation, refrigeration, even greenhouse, for example, all these are under the these are only 250 degrees C. So these, if you are able to produce that temperature, you can utilize that energy. Okay. And then power generation is more than 60 degrees. Even 60, 100 degrees also you can generate power, which is using the organic ranking cycle, they call in thermodynamics. In physics, you learn thermodynamics, for example. So there you learn the power cycles, thermodynamics, engines, Carnot engines, etc. You might study it like there. So there also is 60 degrees, because depending on the working fluid evaporator temperature, if you are able to generate the vapor, you can produce the power as well. So based on this one, low temperature less than 100 degrees, medium, we will say high more than 400 degrees. In thermal power stations, we use more than 400 degrees kind of thing, for example, in VTPS. And then here, what are the solar thermal technology? What my talk is here, morely I will discuss the radiation from sun, then I'll go through the solar collectors, then I will go for the heating, cooling, power generation. So these are how, just I will give you overall information so that you can select which technology you want. Even common person in India, especially our really common people, when the power, suppose someone want to sell a solar panel, solar system, you can question them. You can understand what kind of system you want. Like you will have an idea. Also, you can when you're doing a research also, which technology I should work, what kind of technology I can do research. What kind of problem, what is warranting for this our society, what kind of society is facing the problem. You can choose it from the based on my information. You can select what type of research actually demanding for your needs, kind of thing. So today, now I will go through radiation from sun, how much actually from basics, because Jeevan sir encouraged me to talk more physics related. So in this thermal radiation, when you're reading, when you're studying about thermal radiation, we know electromagnetic waves, electromagnetic spectrum, ideal black body radiation, Stephen Boltzmann-Laka. These are all I think you might have known that, but I will just give you a brief because you need to know how you need to calculate when you're doing a research, or when you're calculating how much energy available in your area, for example, especially in our common area, wherever you have the location is there. So these are the basic summary of this one, because we need to know solar geometry as well, because equator, latitude, longitude, with the location of to find it. And then you need to know some equations, like what is the black body radiation, then electricity. I'll give you more details on this one. See, what is the thermal radiation actually? Thermal radiation is a travels in a vacuum. If a vacuum chamber is there, then it radiates through it's not conduction, it's not convection. So it is transformed in the, for transport that energy from one place to another in a vacuum in a radiation mode actually. So this is the way, even when you are heating, when you are suppose in front of the fire, that radiation comes and then you will feel hot. So then this from the sun, whatever the energy is coming from the sun, you will see the electromagnetic wave spectrum. Here, if in the whole spectrum, if you can see the right side bar, if you look at very different waves, it's a wavelength. Wavelength is very important. So you can see from the here, for example, what we are seeing in the light, that visible range, what is like, something like 700 nanometers or 0.7 micrometers to something like here 400 to 0.4 to 0.7 micro nano. These are nanometers and micrometers. You can see, you can count it. Okay, and then here there is a ray waves, different waves, the gamma rays, microwaves, different rays are there. All different rays in this spectrum is there. But only what we are seeing in this one, in the light from a light source, is in some part of the infrared, some part ultraviolet, and then we have to capture. That means these are very important. These are band gapping. That's why when you're selecting the technology, these spectrum is very important. So here, if you see the color, for example, you are seeing the fire or something, some colors, for example, their wavelength is this range actually. Say for example, violet, blue, VIBGR. If you say VIBGR, rainbow, for example, these are the color in wavelength. Wavelength is very important here. So that's why you can say, if you know wavelength, you can calculate how much energy is coming from the sun in that zone itself. That's why these are the wavelengths are there: ultraviolet, blue, green, yellow, orange, red. These are the various range. If you are seeing red, means that light, that color of that light is in this range. In the house also, there is a radiation is there between the people, between the items, and between holes. Each body is radiating actually. So therefore, every around constantly emits the solar, emit the thermal radiation. Then thermal radiation range was actually 0.1 to 100 micrometers. So then the visible range, as I said, 0.4 to 0.76. Infrared range this one, and ultraviolet range this one. So therefore, the body emits some radiation is visible range is called light source. Light source is the range is this much range only. So then electromagnetic variation and then wavelength is this solar radiation. Solar radiation nearly falls between 0.3 and 0.3 meter for 3 micrometers. So then within this range, then we can split into that one. So this is the whole range. If you look at this small diagram, you can see scaling. When you're scaling whole thermal radiation in that part, some part of that one, only solar thermal radiation. And in the solar, in the thermal radiation, there are ultraviolet is there, infrared is there, and visible is there. Then black body, is a perfect black body. I think you might know that. So that means emissivity and absorptivity is equal actually. So there's here within the hole, black hole. If you put a ray into a small hole in the body, so now it reflects and it transmits, it absorbs everything. There are no losses. That's a black body actually is called. And then actually the black body and real body, real surface, because black body is ideal surface actually. That means perfect surface. This is smooth, very smooth. Any surface material, so real surface, it's difficult to make 100% smooth. So that's why the uniformity of those ray emitting from the surface is all the directions are uniform, whereas in the real surface, the radiation from the surface is non-uniform. That is, you can say, what is the people, if you ask somebody, what is the black body, what is the real body? So here simply you can say this way. And then whatever you are learned, the Stephen Boltzmann concept, these are all related to black body actually. So these are the equations you might have seen. E is equal to a sigma Boltzmann constant. If you know temperature, if you know already this is a constant, then you can calculate how much theoretical energy is coming black body radiation. This is the Planck's law, you know that. I think you might have seen some people who are doing the physics. So there are who are studying the thermal radiation. So the Planck's laws, they should be familiar with this one. Here also, this is based on the wavelength. In the equation, there is a lambda is there. That will you have to put it on a temperature, whatever the temperature is there, then you'll know how much energy is there. So here is the diagram shows Planck's distribution. So you see in the right side, the diagram shows like at various temperatures, at various wavelengths, you can find how much energy is there. So this is the distribution of the energy available. We have the Wein's displacement law. This is also, we can, if you know wavelength and you know temperature, you can calculate either wavelength, you can calculate either temperature, you can calculate from that given information. So yeah, these are all equations. I don't want to go through in detail. This you might have seen solar spectrum. There is, I say, sunlight top of the atmosphere, black body spectrum, and then radiation at sea level. These are ranges, different range. How much energy is available at different black body, real body, you can say that one. Then solar radiation in calculations, when you're calculating, there is a beam radiation that is like a black body radiation, some light source coming from without any filters. Then diffuse radiation, that with scattering, etc. Then total is a global or total radiation. You have to calculate because you have clouds. You have to consider when you are located, say, come on, BGNR college, then you have to see the real clouds. how the clouds appearance, etc. And then those are very important. Shading, etc. Everything is very important when you're calculating the how much energy is available. So here, this is information very important because when you are saying location is very important in this, especially solar when you are designing any plant, selecting. People say, oh, you will get this solar panel produce 350, but you have to question that. No, whether it is available in Kamo or not. The location is very important. So based on the latitude, longitude, and latitude, say Kamo, for example, latitude angle is here, 17 and 18. So in this globe, you have to see which is the longitude and then give the equations in the software that will give you energy. So you have to ask the vendor, can you show me the calculations, please? I like that you have to say that. So because that location is very important. When you say, oh, this panel produces 350, no, it won't, because your incoming radiation itself is very less. Okay, or more. For example, if more coming, we are happy. And then in this, so there are in that equations what I was shown previous one. So the geometry like a equator, and then the location, that's important. So you need to know the geometry when you're designing a system as well. Then the radiation properties. Actually, when you are solar radiation, solar energy, or calculating in especially thermal radiation, we need to know these three parameters actually, three properties of that material: absorptivity, reflectivity, and transmittivity. So how much, even though the radiations, sun rays are coming from there onto the surface and solar panel, for example, okay, how much absorptivity is there? How much energy is absorbing? That is the wave. That's the materials actually, material characteristics. These are material characteristics actually. So the technology depends on the absorptivity of the material, reflectivity of material, and transmittivity of the material. Okay, so you have to carry this is the way you have to design the system. Even the thermal system, if you put the collector, for example, how much say, if I'll show you all these where it plays actually. So here like a normal surface striking on that one, then some part is if it is a real surface, is reflecting different ways. And then see here in incident radiation is coming and reflected back. This is the black body radiation, and then you need to know angles of azimuth angle kind of thing. These are the equations you have to put it. Then black body radiation is a perfect body, is an ideal body, is no, because it's difficult to produce. But whereas gray body is a real surface, you can see here the emissivities of that one. Black body is about 1, and the gray body is in between 0 and 1. So the even variation surface, if you look at the characters, if you put into the measuring this one, you will get this type of trend. Smooth curve tells you black body radiation, there's a maximum you can get it, but the real surface you have to achieve, because when you're designing the material or a collector or so you have to, whether it's close to the black body or not. So you have to improve that material, maybe improve the characteristics. Now after this, I will go through collectors. So solar thermal collectors. So here the sun is coming, and then so there is a collector is there. It's like maybe a panel, for example, solar PV in a panels, but whereas the other types of collectors are there. Solar thermal technologies is basically those are like a mirrors, reflectors kind of thing actually. So like a flat plate, evacuated ponds, in a solar ponds, you can use, you can water, you can pour it, and you can store the energy as well. And flat, I will show details each one. Here the other part is, one is a stationary type. There are even a small one sun. Even you can make 100 suns also you can make it. If the space is ever, that's like concentrated collectors they call. There's a refractive material is involved, reflectivity involved, all these. So whereas in this system you need a axis tracking system is required. Even that one, 2 tracking means polar coordinates, even locally and also both vertically and horizontally you have to rotate according to the sun movement. So there are different tracking systems also there. You can see compound in the single axis tracking system, compound parabolic, the shape of that collector, parabolic shape or parabolic trough shape or a linear Fresnel reflector. So I'll should go through the detail of this one. If you see the swimming pool, they put the some solar thermal collectors on top of that one. Even solar panels, they put it. See, if you look at, and there are heat, solar energy coming, and then you can utilize. That means area. How much area is the important? So that's why we have to see how much area is available, because it's a watt per meter square. That is the energy available there. Then you can collect it and store it in a tank, and you can use bath or a swimming pool, whatever the application, because you need to get there, you have to know the temperature range. So then you have to circulate that much fluid. So this is a flat plate collector, because inside there is a pipes are there actually. So these are coatings are there. This is when you buy any panel, like even a thermal collector, you have to this specification of this one. This is the specification. You have to check the what size of it is, what is the observed film, and tubes, etc. Because these are important for you to check it. And then inside the collector, so there are just we can make our own actually, like a copper tube. We can take copper tube, we can braze them, and then you can put the insulation, thermal insulation below that, and top is glass. You can keep it, and we can make you even out of home itself. Because we use more geyser, electric geyser, we can minimize the electricity while using this solar thermal collectors. Okay. Even especially in Delhi, for example, in North Kashmir area, where they need more heat as well. So we can put these collectors, and then we can extract the heat and just pump. There is just pump required and circulate the fluid, and you can collect the thermal energy during daytime. You can store it also. You can store it as well. Just like here you see a rooftop. Even in the UK, we are building some more like this type of brick-based houses actually, vertically inclined 15 to 30 degrees. So these are the components, whereas in a flat plate collector, okay, the most I will go through. The gaskets are there, headers are there, and you can see the configuration, how inside we can make ourselves actually. Even if you know, you can hire a welder and fitter or something. You can make your own solar collector just by the pipes, and you need to cover with the color paintings, etc. You can make your own. So these are different configurations. Putting the tubes, copper tubes, where you can keep. First one shows the configuration, and then where nearby surface. They are a different way. The arrangement of those copper tubes. This figure shows. Then there is another way, where there is a different way, because if you want to get more hot water, then this is a surface, because you have only one tube, but it's a serpentine type. Because if you suppose if the room if the water enters at 15 degrees, for example, or 20 degrees, then at the end you can get the like a 40, 50 degrees temperature. So that we can. So and you can another way. So manifold type, the parallel seance type. You can arrange the copper tubes inside whatever way you want. This is actually first solar water heater. It was 1902. In that they published this one. This is the first solar collector in US. They have published 1902. And this is the collector, basically in the thermal power stations. So this is the parabolic trough type actually. In there's a pipe is there, and where the white sparks are there, that is the pipe actually. So there actually working fluid is passing through that one, and this mirror shape, that is the mirror shape is there. That is actually whatever the energy comes there, then reflect back to the pipe actually, that linear, that long pipe. This collector, it's about even 5 meters or 10 meters length will be there, depending on the various available. Okay, so these are the main solar thermal power plants. They use it in Gujarat also. In 2014, they installed 125 megawatt power plant using this type of solar collector. But you want to know, when you're selecting these solar collectors, you want to know what surface should be, what coating should be there, what material should be go onto the pipe, what surface going to the reflector. So these are the information is given here. If you want to reflect back, then your reflectivity should be more, or you want to absorb we suppose the pipe where the water working fluid going through that one, where the heat transfer section is there you want to absorb it is more. So depending on the materials, like for example here black coating, there here see, so good absorb material is black chromium nickel plated. So you can see the emissivity and absorbivity. So these are very important, because for absorber plate, the emissivity should be less, and whereas absorptivity should be there. Whereas reflectivity, absorptivity should be less, and emissivity should be more. So that way you have to select the materials. When you're selecting, when you're designing your own system, when you're designing, when you are buying a collector kind of this type of collector, then you have to choose the material. What you have to ask, what coating was there on the surface of that plate, for example. So main design parameters of this flat plate collectors are thickness, coating, glass, because when you put in so many layers of glass, then it's reducing the radiation because of that one. So then thickness of the absorbed plate, that is also important. And the air gap, the gap also very important. Then also other complications, insulation is also very important to optimize your efficiency. So these are the equations are there. If you know the area, then heat losses, you know the temperature available, ambient temperature plays major role actually. If the temperature is high, then your temperature outlet would be temperature. If your temperature is low, then ambient temperature will get the low temperature. So that's how it is there actually. You can use this type of equation to calculate. Then solar concentrating collectors are actually, so they are like, say for example, we are in small area, we are focusing like a magnifying, say a magnified glass kind of thing actually, the solar concentrators. Because in this, these are the terms are there when you're using aperture area. What is the aperture area? So I'll show you. So these are imaging, non-imaging type things are there. So these are different classification of concentrators, like a refractive type and reflective type. Okay. So and then a refractive type is a Fresnel lens, because the light goes through that material. So reflectivity is very important. That the property, material property, that reflectivity important. And then in the reflective type, there's a parabolic or center towers. I will show you all these collectors in the next slide. What is the concentrator actually? Concentration, how can you be there? How you want to say, and I want to use, because you have only one sun coming, say 100 watts per meter square coming, but you need say 1,000 to 1,000 required. So then how much is the concentration ratio? You require 10 suns is required, but area you have very small is there. But you can put the glass on a magnifying glass kind of thing or reflective one, then you can get that much of amount of energy there. So therefore concentrated type solar collector. So because if you have small area is there in a house, for example, you have a small house and there's no space, but you want to say for 4 kilowatt system you require for you, but you need so many solar panels are required, but there is no space. But what you will do, you will put the concentrators on top of that one and the solar panel, because when you all the rays whatever they coming onto the top of the collector and focusing onto this particular area. So I'll show you how it looks like. Say for example, the below diagram shows this is like a cylindrical type. The top is the aperture area. Here the sun rays are coming, and but your collector is here in the bottom. So they only this area is less and this area is more. Collecting entering part is more and the receiving part is less. Then the ratio of that one, that much suns you are getting. That much only. But here is to reduce the material, because here the concentrated solar cells generally what we do to, because they say gallium arsenide is very expensive material to coat it. But if you coat more and more, it's very expensive. But you have to make a small cell. And then what we do, we put a concentrator on top of that one. And then therefore we'll get the same equal amount of the power from that one. So these are the different type of concentrators, like a cylindrical, parabolic trough. Previous whatever I shown you, that is a parabolic trough. And then dish type, dish is like a dish. And then Fresnel the type, and then tower type also. whatever the same dish, if you bring down to the on the earth, you can place it like a dish, and for put the tower on the top of that one. Then it's a heliostat type of action. These are also solar tower they call. I'll show you how it looks like. And these are the important parameters. Constant ratio is important. Optical properties are very important. Optical properties like reflectivity, imaging, and then line focusing is very important, because if a pipeline is there, all the rays, whatever reflect from the collector and goes to the absorber. So then it will be, we need to import that one. So then you have to see which type of system is required. And then you need how much energy using these equations. You can calculate from the receiver. This is like the small left side, right side one is a collector, is a sun, how much energy is receiving. And then you can calculate how much rays are, these are rays, sun rays are going into the collector. You can capture it. You can force it. Like you are making like a small black body radiation basically inside. These are the various equations. I don't want to go through because the people might in the audience, they don't know much about these. They might get bored, these equations. Now I want to talk about the working fluid, because when you have, okay, you have collected some energy and then heat is there, available energy is there, then you have to select what kind of working fluid. So that means depending on your duty. So like a steam generation, for example, because we use our power plants, we use steam. But the steam, you see, these are the coal-fired power plants, the conventional type. A lot of emissions are coming from there. Global warming, emissions. So then we want to reduce that one actually. So in that you might study it in the thermodynamics. The Carnot cycle is an ideal cycle actually. And then I think when you're studying about these are the various equations: PV diagram, TS diagram, then efficiency of the system. I think you know this. Then this in the coal pond, we use the more in conventional power plant, we use coal. The boiler is there, the fire is there. Then the rest of components in the solar thermal power plants, almost solar only we are replacing the resource, we are replacing the heat source, we are replacing with the solar panels or solar collectors. In this boiler part actually, we are changing, design small change, but rest of the components are same. All are same, only because working fluid is just taking care of other parts. This is the way other type of one. Yeah, this is the, when you see in thermodynamics, these are the cycles, these are schematic diagrams appears: boiler, condenser, turbine, pump, this is the closed loop system. You will see these things in thermodynamics in your physics studies. Then you study the TS diagram, where you draw it and you calculate the efficiency of this cycle, etc. And then here is the dryness fraction. Dryness steam means whether it's a dry steam or wet steam. In the turbines, we don't want to allow the wet steam. Wet steam means the dryness fraction, how much quantity of wetness is there, like a pure gas, like a air, dry air, like a gas, steam should be there. So you calculate the dryness fraction. You want to make like a dry gas, you have to go to this turbine. So here, this is the collector. It's a parabolic trough, this one, as I shown earlier also. See, a lot of structures are there. It's not easy, but a lot is a gain, this kind of thing, So the glass, the pipe is like a more glass, because it should be transparent, because whatever the rays are coming onto the collector, that has to reflect back to the absorber. So this is like absorber, the glass one, that white part one. The blue part one is a collector. So the all rays are coming onto the surface of the collector and reflecting back to onto the pipe, and where these rays, we are concentrating on such particular part. So the area is the collector area, this you have to take it, and then absorber area, then constant ratio you will get it. Maybe 1,000 constant ratio, you will get that one. That means all rays, whatever the rays are coming into the area, all are focusing at that linearly onto that absorber plate. So this is, as I told you earlier, the coal plant is there, like a VTPS, Vijayawada thermal power plant, or Palwans are nearby, or other power plants are also there. So only thing is the other components are same. Only just you have to change the coal to the coal, that coal firing combustion system to the solar system. The other components are same. Just but you need a space is more here. Okay, but other components are same. Most all the components, only these collectors are you have to change. So, but here actually we need a storage tank also, because the sun is available only morning to 6 o'clock to evening 6 o'clock, say, so sometimes we are in during winter, so storm time, there will not be much sun. So, but you need a storage tank as well. So if you have storage tank, if you have a solar collector, then you can produce power like a coal power plant or nuclear power plant. So here there are different, this is the cycle, different parts of, you might have seen thermodynamics books. You can see this type of diagrams with a solar trough power plant. This is the system schematic diagram. You see solar field. Solar field means solar with the solar collectors. That is solar, that thermal energy collecting, and we're making a steam, and also partly it go to directly to the steam turbine, and then it will go partly go to storage tank. Then we will produce the power here. Here, the different numbers are there here. Pressure, temperature, these are very important when you are designing a system. So this is like a tower type. Here, see, like on the surface of the ground, we place the reflectors. All reflect surface on the top of the tower, where that is like an absorber is there. So it's like a dish. You can it's like a dish. So it's like a dish design kind of thing. So all rays are coming and focusing onto the white part where top of the tower. That all rays are going there, and then we are heating that point where we put the. But you can reach the temperature up to 1,000 degrees. 1,000 degrees you can reach there. 1,000 like nuclear power plants. Yeah, we can use that. So, but design all you have to design on these. So in softwares we use, there is a ray diagram softwares are there. You with help of that software, you can design where you want to place these reflectors, or what space is important, how it will, all our rays are how they are going. But when sun is moving, these reflectors also will move, but the tower will be constant. Because all rays are there, then it will produce the thermal energy, the steam, and then that goes to the power plant. So this is how it looks like. See, the all rays are concentrating to the top of the tower, and rest of the part is same, goes like coal power plant. You can achieve 1,000 suns, 1,000. Even see maximum temperature you can achieve with the help of this one, 1,000 degrees C. But water steam only generate up to 40, 50, 400, 500 degrees C. But we use the thermal fluids, like even bring lithium bromide, salts, that based systems we use that one to get the 100,000 degrees C. Because if the efficiency, the temperature is higher, that efficiency of the plant will be higher. So this is how it will place that reflectors. Sun comes, and then it's the location of the placing location is a critical point here actually. Then this is the diagram. Similarly, only the part of the tower diagram, the solar field is different from the solar trough. So here, this is the way you can see because here you need to know ray analysis. Ray analysis you have to do it when you are doing research, when you are designing a system. The ray, whenever the rays coming to the surface of the reflector, whether it is reaching to the tower point, top of the point where the absorber is there, that whether reaching or not. So you have to place, you have to track the system, full system you have to track. That means movement of these reflectors, like a radar. Radar, when you radar moves, same concept we use for these reflectors to move the according to sun, because there is a sensor will be there. The light sensor will, in the light shadows, if the light is not falling into that sensor, then it will automatically moves. There is a motors are there, mechanism there. So this is the way, because in the center, in this is like the big circle shows the reflectors area, reflectors placing, and where in the small circle there is absorber. So it's not like a center, but it's a like eccentric way where they put all the say. Hello, sorry. Yeah, it's small, only 5 minutes, please. It's okay. Hello.
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 Okay, sir. It's okay, sir.
Because this part is very important, solar cooling, because for India, solar cooling is very important. I will go through that one. Is that okay?
Okay, sir.
Yeah, thank you. So solar cooling, this is because for our Indian climate, we need a cooling, actually solar cooling, but only heating. So far, only we heard about heating, but now cooling. So how can we do? So the use of this, refrigeration, because food preservation, the comfort cooling, air conditioning, for example, if you want to use, so how can we use, because we can use the solar energy for a cooling purpose. So, but in India, we are less using that type of system actually. But we see how the system would be work here, like a vapor compression system. For example, we have a vapor compression system like refrigerator. What are in our homes? We have a refrigeration system. You might have seen our refrigerator. Our refrigerator works on this principle. Like just condenser is there. Condenser means if you see the back of the refrigerator, there is a coils are there. That is the condenser. Whereas the evaporator, wherever you are put storing, that is the evaporator inside. There is a small plate will be there inside. So this is the inside the, and the compressor is the backside. There is a noise comes from there. That is the compressor. So where you can see this type of, this is the conventional type actually. This is a normal refrigeration system. Okay, and even condenser also we use same thing, because in where we put the this evaporator is a cooling point actually. Evaporator is a cooling point where you can freeze it. Where you see in the refrigerator ice forming, the evaporator near evaporator will form, because inside the fluid, what happened when the expansion taking place, then it gets very cool. That means like your ambient temperature is like about 20 degrees is there, but when is the cycle go through it, it will become about 10 degrees or 8 degrees. Our refrigerator system, domestic type systems are designed for 4 degrees, 5 degrees, but when you open the door, it will not stay maintained. Please remember, don't open the door and keep up with that just like that. Your refrigeration food will spoil it actually. But what I'm saying, they actually for the compressor, it takes the electricity. So therefore, instead of using instead of the electricity, you can taking the main supply, you can supply from the PV panels. So this is the conventional type, you can use it. And also these are the thermal system. This is a thermal system where here is tubes you can flat feed collector, evacuate tubes or collectors, you can use it. And there is a heat exchanger is there. Then there is absorber is there. This type of system you can, this is called a vapor absorption cycle is one. This vapor absorption cycle you can use it because we have that is the compressed based system. This is a thermal based refrigeration system where you can tap the extract this thermal energy with evacuate tubes or a flat plate collector or whatever depending your temperature range. Then you can this is like a refrigeration system. This one, the air here absorber is there, evaporator is there. The other only heat exchanger part is different. So here in our in India there is a Thermax is their system. Thermax is there in India, or in Pune there is a company is there. They are producing this one. What actually here there is a pipeline is there. See here the corner side, the top of the corner right side, there's a pipe, inlet pipe actually. The steam goes into that one, and it is evaporate the fluid, and then it will again condense it and again evaporate it. So it's a cycle of completing as for this diagram. So this is our Thermax in India itself. We are producing this type of, but we are not using. Even our cold storage power plants are more on the compressed based systems. But when we have a thermal energy from solar energy, you can replace it. We can contact the people. Oh, can I use this one? Because you can reduce your bills. But initial cost will be more, but you won't get the bill. So this is the diagrams are there, and this is the inside cycle system. There is all components are there, various working fluids are there. I will, if next time, if I'll talk to the J1 sir, and we detail the refrigeration part, or heating part, power generation part, we can work on that one. So these are the various working fluids for the selecting ammonia or whatever the H2O, even water we can use as a working fluid. There are different working fluid. You can select this one depending on your temperature range. Evaporation, boiling point, because you want to evaporate. Because boiling point important. So boiling point, when you know that at that particular pressure, particular temperature, Then you can select what type of fluid you want. And then here, see, the solar energy is coming out to them, then it is evaporates, it go to the vapor generator, and from vapor generator to the condenser, and then there is a throttling device. This throttling device is a pressure changing. They are actually, due to pressure changing, then you're getting cooling effect. So then evaporator, that whatever they are, the cooling part, this is like a plate, and that they surrounded by the food content that radiated that energy into that one. Or so then it takes, then again go back to the absorber, then again go to the indexer, then it will go back to this. So this is a small, you can use it as a cooling. So whereas these are the geometries, more working fluid, lithium bromide we use mostly for the big power plants, big refrigeration systems. So even for the collector here, what type of collector, even depending, as I said, different temperatures, you can use this type also. Dish you can use, and you can thermal energy you can capture, and you can heat that fluid, working fluid, and the refrigeration you can get it. Even both combined heating inside, for example, if you want a bath hot water, is a geyser. You can change the some pipeline to the geyser, some pipeline to the refrigeration portion. Then you can produce both heating and cooling. So then process in our agriculture sector, we use the more drying process, process heat actually. So these are the process of water heating, cooking, refrigeration, so various technologies. Yeah. See, this is the heater, hot water heater. This is the diagram shows. And here the drying process of food, even rice, for example, even mirchis, for example, you can, this is the way you can make configuration at your in a warehouse itself. You can allow because the plastic transparent sheets, you can put it and make it like a box, and you can, like here mainly we have to consider like a humidity, temperature. These are very important for the fluid. So these are the conflicts, because even for drying also we can use solar energy directly you can use it. See here another diagram, second diagram shows, see the humidity air goes to there, then you put some food there and you dry it. Here there is another classification of dryer. See, they are using the different air, because you have to design such a system that how this hot air goes through that fluid, because when the hot air goes through that one, because we'll enclose it, and then we'll allow the sunlight to come to that one, and you pass through the air, maybe a blowers you can use it, and then pass through the fluid, and then you can dry your food, because you can minimize your fuel, diesel utilize the conventional fuel sources. You can reduce that one. You can then solar cooker. Solar cookers. I think solar cooker as well. Even so, cooker food you can prepare your food as well. So this is the typical type of solar cooker. For example, you can it's like oven, but we can use it. But in our Tirupati itself, there is a gained solar cookers are there. When you go to Tirupati or Shirdi Sai Baba, Shirdi that ashram, you can see the solar cookers, gained solar cookers are there. They are serving the whatever, if anybody is going to the Tirupati, and whatever the meals are serving, they are using solar energy. They are serving a lot of, there's a one expert is called Gadia, Deepak Gadia from Gujarat. He actually designed this system. Actually, he's doing a service. So there's a guy, I'll show you that pictures later, but I could not find that one. But I'll show you an example. Even desalination. Desalination, because in our Khammam area or Nalgonda area, a lot of salt water is there. Okay, if you want to purify water, like even salt in Dubai, Kuwait, other Gulf countries, they are making pure water from using sun energy. This is why can't use we? Our government is why not looking at these things? So because we are only, so therefore I think there is some political what they are important. The priorities are there, they are using. So but desalination we can use it. Only you need to heat that water and evaporate it and then condense it, and you will get pure water. But you have to design a system. Either in Dubai, other Gulf countries, they are using this desalination, solar desalination. But in Khammam, wherever the salt, the waters are there where we can use it. We can get the pure water. So methods of purification, there is a different technologies are there, diffusion still, chimney type, multi-effective base, and still there are different techniques are there. When next time, if J1 sorry, allow me, next time, if anytime, I can give each technology, I can train the students. What kind of we can design, even if the students want to take a project like a purify water using a solar energy, we can take a project. And then we can develop the technology within the, we even, I'm guiding the students here to develop a the own system, solar system using purified water, because there are some Dubai students, my MSc students are there. I'm guiding 6 students. They are using this type of technologies. So here, see, there are just you have to evaporate the water, that one, then condense it. But different configurations are there. Okay, so this is the book gives you actually full details of this solar thermal technologies, the Duffy and William. You can get more information if you want. If you want a design system, you can, even when you have knowledge, you can ask the vendor what type of technology I want, why I want to use that technology. But when you have idea of using those various technologies, you can ask them. So thank you so much. I might be late for the next session. Hello.
Thank you very much, sir. A great, we have exposed to a fantastic and very useful research outputs in the solar electric power technologies. Really, we are very happy to hear this, sir. And also, from the beginning, actually, the physics which is involved in the solar power energy or solar power technologies, and also how to capture the energy. There is plenty energy in the universe. How we can capture the technology you have explained very well, and also thought-provoking and also research-oriented sparkles you have given to us. We feel, sir, and really it's a great day, but time is very short. The other esteemed speaker is waiting to deliver a lecture. Before that, I am promising you, sir, under your noble guidance from our SR&BGNR Government Degree College, we do research. We do research, or otherwise we do a project work under your noble guidance. I feel that should be a set to us. We are very thankful to you, sir. We are very thankful to you. And the next, any doubts, any questions from anyone? Or otherwise, time is less, and then after we can discuss. The sir is waiting. I'm inviting my colleague, research scholar and assistant professor P. Anita ma'am to invite and introduce the next speaker, esteemed speaker. Thank you, madam. Thank you very much.
Thank you, Jeevan sir. Thank you so much
sir.
For giving an opportunity to explore.
That's our pleasure, sir. That's our fate. Thank you, sir.
Thank you.
Good afternoon, everyone. This is a great privilege to me to introduce Dr. Jammu Ravi. The Department of Physics is very much positive about encouraging the interdisciplinary subjects. And so we have invited Jammu Ravi, sir, who is basically a chemist. He is working as a scientific officer at Indira Gandhi Center for Atomic Research, Department of Atomic Energy, Kalpakkam, Tamil Nadu. And he is working in the field of spent nuclear reprocessing and allied radioactive waste management. His area of research includes the synthesis of advanced solvents for the separation of actinides and lanthanides. evaluating the radiation stability of the solvents during extraction, hydrodynamic suitability of solvents, and various radioactive radioanalytical techniques. And he acquired his master's PhD degree from Homi Baba National Institute, Mumbai, and he was published 15 international papers, and also he has best presentation award by Royal Society of Chemistry in the international conference for the plutonium futures, the science held at University of Cambridge. He also worked as assistant professor for chemistry in various affiliated UG and PG colleges. He is also a good orator to motivate the students towards the research. And from this brief introduction, I am inviting Dr. Jammu Ravi sir. Over to Sir Jammu Ravi sir. Sir, please speak. Speak on this webinar, sir.
Thank you very much. Thank you, one and all. First of all, thank you for SR&BGNR Government College.
Yes, sir. You are audible, sir.
Yeah. Today I'll be talking briefly about fundamental particles of the nature. I request me, please allow me to share these slides. I have a problem in sharing the slides.
Sir, you can share now.
Sir, actually I am having two logins through my PC and phone due to connection. So please allow the other Jammu Ravi who is there in the participants, please enable.
Acha, sir, 1 minute.
Yeah.
Yeah, now you can do it, sir.
Yeah.
Hello?
Yeah, I'm doing. First, before starting my session, I would like to appreciate the college for arranging such events for the benefit of the students, and management of the college for encouraging such activities. This will really help the students to get the exposure outside. One minute. Hope you are able to see my PowerPoint presentation.
Yes, sir.
Yes, sir. Yes, sir.
Yeah, this is Jammu Ravi, working in the Department of Atomic Energy. Just before going to the full details of my presentation, just I would like to give the introduction about my department and what are the activities and how they will be useful for the students. What are the career opportunities that are available in the Department of Atomic Energy, ILNCs. And then there are certain workshops which are conducted by Indian Association of Nuclear Chemists and Allied Scientists. It's an association of Indian nuclear scientists. So this association will arrange workshops for the students of right from intermediate, degree and PG levels. So those colleges who want to know more about the nuclear aspects and those who want to conduct educative sessions, they will be conducted by this association, and it is at free of cost. You don't have to, no college has to pay anything, and even you don't have to give the transport charges. All the charges will be borne by this association, and the senior scientists from our department will come and explain the basics of nuclear chemistry by theory, and even one session they will demonstrate the practicals and the demonstration will be done by the students. So the senior scientists will make the students the experiments, and the students will participate in the experiments. So such kind of a series of experiments and workshops can be arranged by this association. So your college, if you are interested, and this association will be available, you can make use of this service and let the students be benefited out of the society. And apart from that, now in my presentation, I'll give a more general way. Students of physics, as you have to know that I'm a chemist, but I'm in the physics forum. It is because of this radioactivity and the subatomic particles. So actually, after all, it's a science. We are dividing that into chemistry, physics, and other whatever name you give. Basically, we are trying to understand the nature. Okay, we are trying to see what they are in different aspects, but science does not vary. So in my talk, I'll just give very brief. It will not be so many fundamental, so complicated theories. They just I will touch upon, since UG students are also there. I don't want to go more details and confuse and overburden to them. So it will be very light and very simple. And I'll touch upon this radioactivity and origin, how that radioactivity, why certain elements are exhibiting this radioactivity phenomenon. That we will talk by understanding subatomic particles which are present in the nucleus or in outside the nucleus. And then I'll just give more attention rather to on the excitements of physics. What are the challenges that the physics students can take up? What are the opportunities that physics candidates are having in pursuing the fundamental sciences? And with that, I'll just conclude. So to start with nuclear Department of Atomic Energy, we are dealing with the nuclear reactors. Just now, the extensive lecture was done by Prabhakar Rao sir. He was very well explaining about the sun and solar systems. And sun is the greatest nuclear reactor where the nuclear fusion reactions are taking place. And the sun is a natural nuclear reactor where the nuclear energy is coming in the form of heat and radiation to entire planetary system. And here, the Department of Atomic Energy is having nuclear fission type of reactors. So in our India is having a vast resources of thorium, and we just wanted to make use of this thorium resources. Though, as sir rightly said in the previous lecture, that India is having so much of potential to use solar energy, we are till to the develop to utilize full capacity. And not only that, the technology has to be improved a lot. And but if you see here in the thorium, which India is having plenty of resources, if we use this thorium based reactor, then we can sustain the power. Since that India is having large population and we have so much demand for the electricity, all means of energy sources must be utilized in an effective manner. So in order to use this thorium based fuels, first we need to have fast reactors, and to use the fast reactors we need to have more plutonium, which are plutonium based reactors. So to generate the plutonium we need to have uranium of the first type. Here we have you can see the PHWR reactors, which is normally first stage of the reactors where the natural uranium is used as a fuel. And the blanket of this nuclear reactor we get plutonium, and the plutonium thus generated from the PHWR will be used in the second, this yellow colored reactor, where the plutonium is used as a reactor fuel. And at the periphery of the fuel core we will use thorium, and there that thorium will be converted into uranium-233 in the nuclear reaction. And that uranium-233 will be used as a fuel in the third stage, where you can see the other stage number 3. So this is how the nuclear power program was envisaged by Dr. Homi Jahangir Baba. So we are still working in this plan. and we have successfully demonstrated the first and second stages, and second stage to third stage conversion we are there. So thus the Department of Department of Atomic Energy India is having various opportunities and challenging careers to pursue, either for all streams, right from engineers of all branches and sciences of all branches. And for the students who are doing MSc, if they want to pursue PhD, we have Homi Bhabha National Institute, deemed university, which is a part of our department, which will offer PhD degrees. So after your completion of MSc, you can appear for the entrance and clear interview to get the admission into HBNI PhD. Then you can complete your doctoral program. So and those who want to pursue the permanent career after the immediate of your PG programs, after MSc program, you can join in a Bhabha Atomic Research Center, Mumbai, BARC training school. There you can, if you clear the same written test and interview, if you clear, based on the Government of India norms, you will be selected as a training school officer. Once your training is completed for the first year, you will be taken as a scientific officer, and permanent position will be given in the department. So after your MSc, be thorough with your fundamentals. You can do your PhD, and you can join as a scientist in the department. And those who are there in the PhD completed guys, who can join as a KS Krishnan Research Associate. After completion of your PhD, you can apply for this position and get the higher levels of the scientific position in the department. And suppose the students who want to do with the BSc, for those who are doing in a BSc who are not in a position to go for higher education because of any reasons, or who want to join in the department, who want some job and the government job, they can join as a CAT 1 trainees. So here even +2 students, those who have passed your intermediate, those can join as an assistants and lower category, that is CAT 1 and CAT 2 trainees we call. So you even right from the intermediate to degree, PG, PhD, all streams of the students are having the opportunities in the department. So make use of them, and you can get the career at any level you wanted. Okay, so with this I'll go into the subject. Normally the radioactivity, which we call, many people have the fear that Department of Atomic Energy is handling with radioactivity, there may be nuclear reactor, is a little dangerous. Some kind of misconceptions is going on around the society. Right from our childhood we were seeing this, but actually the radioactivity is nothing to do with your reactor or some other facility of Department of Atomic Energy. Radiation is there everywhere. As in the previous talk also, we have seen how the sun is exhibiting various kinds of emitting what kind of radiations. You see in and around to us, right from the earth, you have several isotopes like thorium, uranium, radon, all this kind of earth crust, and even in the air, atmosphere, everywhere you have one or the other isotopes which are emitting continuously the radiation. Apart from these, you are seeing the radiation from the cosmic rays from the solar system through the entire universe. This radiation is there. So if you see the quote, life on the earth has developed with an ever-present background of radiation. So that is what the background is. By default, background is the radiation. So it is not something new or invented by us. So we have to live. It's a part of the system, and we the part of the universe. So we have to understand it. When we understand more, the fear will go. When we don't understand the system, more and more insecurity, the fear will be developed. We will see why certain amount of elements, why certain amount of atoms are exhibiting radioactivity. What is the major source of this radioactivity? We will see with a little more, since some of you are done with your in PG, you know that the binding energy in the inside the nucleus. So as a chemist, what we do is do chemical reactions which are outside the nucleus. So we always talk about the electrons, the electronic interactions, compounds from the atoms, how the molecules can be synthesized. Those kind of aspects will be dealt with us. But when it comes to the nuclear aspects, it is inside the nucleus, inside the atom. So whichever atom which is not stable will emit the radiation. And then in our present talk, we will try to understand what are those particles inside the nucleus making the new atom unstable. Why these atoms are exhibiting radioactivity. It's a fundamental, very basic aspects we will see. As we all know, the binding energy inside the nucleus, all the nucleons. Inside the nucleus, as we all know, that neutrons and protons will be there. Outside the nucleus, you have electrons to counterpart the charge. And that when I'm talking about a nucleus, I'm dealing with neutrons and protons. So the neutrons and protons are occupying in a very small volume with very huge force, and that force is that energy which is keeping them together, we call it as a binding energy. How this binding energy is coming? Suppose you take the mass of the proton, it is 1.00727, simple unit, atomic mass unit. And when you take up a neutron, it is having approximately same mass. But when it is forming a nucleus, when it is forming an atom, so say for example, one helium atom is there where you have 2 protons and 2 neutrons, mass 4. So you will expect the mass of this should be the product of 2 into this one plus 2 into this one. But if you really see the net mass, there will be a defect. There will be some mass missing. That mass missing is nothing but the delta mass, what we call mass defect, that is responsible for keeping them together. So that is what we call binding energy. So if you can see the binding energies at the lower atomic, see this plot is showing binding energy per nucleon. Suppose if you have 10 nucleons inside the nucleus, we are just dividing that total binding energy by that 10 as a function of mass number. So at this bluish region, if you see, the binding energy is lower, and as you are increasing the mass number, the binding energy is increasing. Means higher the binding energy, higher will be the stability. So this region is trying to prefer this region. Means it is trying to occupy more binding energy per nucleon stage. That's why at the lower mass particles will undergo the nuclear fusion reaction to form a bigger nucleus, and because of that there will be a tremendous amount of energy will be released. That is what is happening in the sun. Inside the sun, 2 hydrogen nuclei are undergoing the nuclear fusion to form helium or hydrogen gas, or the fusion reaction is taking place. So this region is fusion. Now if very high mass numbered atoms if you take, they will be again having lower binding energy per nucleon. So they will also try to occupy this higher stability region. During that that condition, the nuclear fission will take place. So they will try to occupy this more stable region. So this is what the relation between the number of protons and neutrons. If more number of neutrons are there in the nucleus, what will happen? When more number of protons are there in the nucleus, what will happen? Suppose protons are charged particles, as you know, it's having a positive charge. But how these positively charged protons are together inside the nucleus, very small size nucleus, that we will see and come back here later, little later. So in the fission process, what is happening? During the nuclear fission, for example, you take a uranium-235 one element, and if you are bombarding with one particular neutron, it will undergo the fission. It means the 2 fragments will be formed, and the 2 neutrons will be released. 2 to 3 neutrons will be released in general. So during this fission the sum of masses of these fission products is less than the mass of the initial one. That means there is a mass loss. That mass loss is converted into your energy. So this energy will be very large even for a small mass loss. Even the amount of fraction of mass that is lost is very, very small. but still the energy will be very, very high. Why it is happening? This all you know, the energy relation with mass is E is equal to mc square. Even though m is small, c square is very large in quantity. Therefore, small amount of mass will be equivalent to huge amount of energy. So that's how the nuclear fission reaction in general it takes place. So yeah. Then coming to the particular topic now, when we are working in the Department of Atomic Energy, we will be dealing with the fuel fabrication, means uranium or plutonium or thorium, whatever the fuel it is, we have to fabricate the fuel. And during this fuel fabrication, we have to deal with the radioactivity that is being emitted by those fuel materials. And even after the during the nuclear reaction, the whatever fission products form are also having radioactivity. They also will emit the radioactivity because of the instability or instability inside the nucleus. And there we have to deal with the radioactivity. In addition, during the nuclear reactor operation, all the amount of fuel which we kept in the nuclear reactor will not undergo the fission. Only certain part of it will undergo. Even that will be very smaller, like even 2 to 3 atom percent itself is very big achievement. So normally 1 to 2 atom percent range only the fission will take place. So that means remaining all the fuel will be as such, and part of it will take the neutron, absorb the neutron, and it will become higher nuclides. So means if you keep uranium inside the neutron, some amount of the uranium will undergo the fission, but some amount of uranium will absorb the neutron and convert into higher elements, heavier elements like plutonium, neptunium, americium, kind of things, but with a beta decay. So when we are dealing with, when we want to recover the unused uranium and plutonium, we have to deal with lot of radioactivity. So irrespective of all the process, even in our department, we produce nuclear medicine. There are many isotopes productions will take place for the societal benefit. Outside, in addition to the nuclear reactor operation, we do certain societal beneficial activities which we do. So during those operations also, we will be dealing with the radioactive elements. So radioactivity is very common, and this radioactivity is coming from the atom inside the nucleus. Therefore, understanding the structure of atom is important, and that structural aspects only I am going to share. So what actually atom is? We all know at the early beginning, matter is made up of molecules, molecules are made up of atoms. And now during Dalton's time, atom suppose was assumed to be the smallest particle, but it is not so. Later on, we discovered so many subatomic particles, especially that electrons outside the nucleus and inside the nucleus. And later studies have proved that inside the nucleus there are certain particles. So they are neutrons and protons inside the nucleus. So you can, if you can imagine, this is a ball kind of thing which is present inside the at the center of the atom, and outside the atom the electrons are continuously revolving. Okay, out of this, you know, protons are positively charged and electrons are negatively charged, which are there apart from them, and along with the protons you have neutrons inside the nucleus. And this during your school days we have seen this alpha Rutherford's scattering experiment. In his experiments, what he discovered, what we got the information is that inside the nucleus, that when you take very large sized atom, the nucleus is very, very small in size. Because that's why when the alpha particles are incident, lot of them have simply passed through the atom. Only at the center of the nucleus, few of them are got backscattered. Means the lot of atom, the space, if you total out of the total space in an atom, majority of the space is empty. Only inside the nucleus, heavy dense particles are there, that are the nucleons, and outside the nucleus, majority of the space is empty, and electrons are revolving in that particular state. Okay, to have a feel, let us see the typical values. What will be the sizes of this nucleus? What are the sizes of the protons? If you remember, the size of the atoms will be in the range of angstroms. 1 angstrom is equal to 10 to the power of minus 10 meters size. And inside the nucleus is the still smaller, and that will be, you can 10 to the power of minus 4 times smaller, or you can, if you imagine 1 meter of 1 meter ball or sphere, if you imagine that this is a ball of 1 meter, this will be outside the atom will be 10 to the power of 4 meters. That means 10,000 meters. So it is of that range. Of course, you know, all will not be of the same side. And one more important thing is, inside the nucleus is having a very, very high density. Total mass that is coming from the of an atom is coming from the nucleus. You can see the values also here. Even you know the density of water is 1 gram per ml. If you take 1 ml of water, it will be 1 gram. If you take the lead, which we normally think the lead is more dense material, it is having 11 grams per ml. But if you see the nucleus density, it is 18 into 10 to the power of 13 grams per cc. So such a huge dense nucleus is there at the center of the atom. So the total mass, you can see the total mass of an atom is completely arising from the nucleus. So let us try to understand what are the nucleons and what they are made up of. So we were discussing about the nucleons are nothing but protons and neutrons, but they are not so. These nucleons are not independent particles as such. Again, the neutrons and protons are the composite materials. They are also made up of some other subatomic particles, which we call quarks. So quarks are now the most fundamental particles, which are building blocks of your protons and neutrons. When the protons and neutrons are building blocks of atom, they are the building blocks of the matter. But we don't know. Even the technology improves, the quarks also may be having some subatomic particles. But as on date, the quarks are assumed to be the most fundamental particles. And now, just if you really see the structure of proton or neutron, this proton is having 3 quarks. There are actually quarks are of majorly 6 flavors they are having, 6 types of quarks: up, down, charming, top, bottom, strange. These are all peculiar names of were given to quarks. Now, out of all of them, we will be mostly dealing with up and down quarks because they are the building blocks of these neutrons and protons. Now, if you see the proton is made up of 3 quarks. That is one up quark and one down quark and 2 up quarks. Whereas in the neutron is made up of your 2 down quarks and 1 up quark. Okay, so these 3, suppose if you take the mass of a proton, the mass of the proton must be equal to the mass of 3 quarks. Suppose if you add the mass of these 3 quarks, it should result in the mass of the proton. But because even one important point to be noted is electron mass is very, very small. It is just 0.05% of the nucleon. So you can simply assume that the total mass of an atom that is coming only from the nucleus, and they are from the nucleons. Now, when we are talking about the nucleons, if you see the masses of the up and down, up quark is having a lesser mass compared to your down quark. Suppose up quark is a 0.002 giga electron volts, and this down will be 0.005 giga electron volt. But nevertheless, forget about all those values. But for a simple layman understanding, if you take the mass of 2 up quarks and 1 down quark, it should be equal to the mass of the proton. But in reality, when you do it, 2 up quarks and 1 down quark is only just 2% of the nucleon. That is proton. That means what? This is the proton. Proton is having only 3 quarks. And now if you take the masses of all the 3 particles, they are not amounting even 2% or 3% of the mass of the proton. Then what is the rest 98% of the mass coming from? Proton is having only 3 quarks, and all masses of all the sum, you take the mass of your 2 up quarks and add to the 1 down quark, and the total mass is just 2%, and remaining 98% of the mass is missing. Where this mass has gone, that we have to understand, that we will see in a coming slides. Then how these quarks are reside inside the proton or neutron. These quarks are having very, very high speeds. The speeds are almost equal to the speed of light. Okay, I have given the value also here. And what is the volume of this proton? This proton size is 1 femtometer. Femtometer is 10 to the power of minus 15 meters. Very, very, very tiny, small size. Within that very small size of this proton volume, your 3 quarks are moving with very high speed velocity. See, being a physics students, you all are aware when such a huge speed will give the motion. When particles are in motion, you can imagine the force the energy that they have is kinetic energy will be very, very high. And such a high kinetic energy particles are residing in very small, tiny volume. How this is possible? See, when you see that is be possible only because of the strong force of attraction. You know how to make very high kinetic energy particles, making them together, binding them together requires a lot of force. That force particles, something is operating, some force is keeping them together. Highly fast moving particles or reside in a smaller volume by a strong binding energy. That binding energy is amounting to your 98% of your energy mass. Hope you are not confused. See, I told the mass of the the sum of the mass of all these quarks is amounting only 2%. Rest 98% of the mass of the proton is missing. And we have noticed that these high speed particles are residing in very small volume. That means there is a very huge and crazy force that is making them together. That crazy force, that crazy amount of energy is resulting in the form of mass. I am saying energy in terms of mass. That is E is equal to mc square. Many people say that, but if you really see the Einstein's original paper published by him, it is not E is equal to mc square, but m is equal to E by c square. The meaning, mass is resulting from the interactional energy, right? Mass and energy are not same. Mass is not something independent. It is just the consequent of the interactional force, interactional energy. This interactional energy, which is keeping these 3 quarks inside a small volume, that is very, very high. That amount of interactional force is very high that it is amounting to 98% of the mass of this subatomic particle, that nucleon, that is proton. That is same for the neutron even, where the only difference is in place of 1 up quark there will be 1 down quark. That means energy and mass are same, but to be more precise, mass is a consequence of interactional energy. So these 3 nucleons, these 3 quarks which are present inside this nucleus are attached with so much amount of interactional energy, and this interactional energy is also having in a particle nature. It's not a radiation, and that particle what we call is gluons. Okay, so the gluons are the particles which are exchanging this force between these quarks, that making them more stable. So there are another particles which we are heard now is gluons. Gluons are most fundamental particles inside the proton, which is keeping the quarks together. Just a minute. Thank you. And in previously we have discussed that the mass of the density of the nucleus is very high, and that density is uniform. The density is uniform throughout the nucleus. What does it mean? If this interactional energy is different, and if it is operating only inside within them, and at the very core of the nucleus, there should be very strong attractional force, because it will experience so many interactions from the surrounding quarks or nucleons. But see, the uniformity in the density indicating that the nucleus force is almost same in the entire nucleus, which means in addition to this short range forces, there is something else which is operating, that is weak forces operating. Those weak forces are of again given as Z and W forces. You know this, we'll talk little about them little later. Now there will be a fundamental question that will be asked during the school days. What is this mass at all? How this mass comes? Mass is a what actually what difference between mass and weight? When we ask the students of the school or college, they will be not clear. But even today also, the concept of mass is not so clear. Mass is completely independent of gravity, we say. Mass is something to do with the nuclear forces or the total forces which are present inside the system of the subatomic particles. So if I have to give the mass, if I have to define the mass, I can define it as an inertial mass and gravitational mass. Inertial mass is nothing but the mass which is resisting my acceleration. Am I audible?
Yes, sir. Yes, sir.
Yes, sir, it is clear.
Yeah, okay, thank you. I'm calling inertial mass is the mass of a subject object which will oppose the acceleration. That is the inertial mass. So the smaller object will resist less, so it is having less mass. The very big mass object, like a very big vehicle, when we are trying to push, when we are trying to give acceleration, it will resist the acceleration. Therefore, we say it is a high mass substance. When we are talking about weight or normal gravitational force, what is the charge of this gravitational force on the object? That will give you the mass. Now these two masses may not be same, they are not exactly same. So you can take up such an understanding the mass is a fundamental concept that you can see. Now we heard about something about quarks, that quarks up and down which are present inside the nucleus. But apart from, in addition to these quarks, you have 6 quarks, that is up, top quarks, and on contrary to them, these up, and top quarks are having charge plus 2/3 charged particles. On the other hand, down strange bottom quarks are having minus 1/3 charge. Suppose if you take a proton, 2 ups and 1 down, 2 2/3s plus minus 1/3, you will get a plus 1 charge on the proton. And if you see the neutron, 1 down and 2 ups. So if you calculate this one, 2 minus 1/3 and plus 2/3 will be 0. So neutron is a 0, so no charged particles. Though you have 6 types of quarks, we will see the up and down quarks only, and they are all the time in bounded condition. Free state, you will not see the up and down quarks, and all other quarks are having very high masses. I have given the masses of each quark here. You see the top quark, which is having a tremendous amount of mass. This is energy. Energy is nothing but mass. So this is having a tremendous amount of mass. Why it got a tremendous amount of mass, we will see. And this, because of this high mass, it is highly unstable. So as soon as you try to make it synthesize through the accelerators or by any technology, it will readily undergoes dissociation. It will not be in a stable condition. So it is highly unstable. You will not see it in nature. If you found any good research career, if you want to do, yes, that is more exciting. and you will see only the lower mass containing quarks, which are very common in the nature. So they will be there in a bound state. Remaining all are having unstable, and therefore they will not do. And now you see, during the beta decay, what we call or positron emission, beta is electron, and the antimatter particle, if you take, that will be a positron. During this decay of a positron, what is happening is proton is converting into neutron. This see here proton, and this is what neutron. How this proton can be converted into neutron is simply by the conversion of one quark. Down quark is becoming up. Up quark is becoming down quark. Then because of that, it is possible to have. So that is what here happening. Up quark is converting into down quark with the releasing of the forced particles, the weak force particles, that is W plus. So again, this is undergoing to give your positron and as well as neutrino. We will see neutrinos also a little later. So bottom line is you have 6 types of quarks which are operating. And when we are talking about fundamental particles, many people say K-type mesons or bordons or hardons, or you will see n number of particles. All these n number of particles are basically made up of these constituents. So they are all just composites of all these quarks. And as on date, quarks are fundamental, and we don't know what are they inside. And outside the nucleus, you have electrons, which are leptons. So again, leptons are also not the same. The most common lepton which we see is electron. Okay, and electron is very, very small mass. So and even electron is assumed to be independent. It is not a composite material as on date. We don't have any structure of electron. Electron itself is assumed to be the fundamental particle. And this muon and taus are again the same of this kind. They are also all negatively charged particles. They all will exhibit electromagnetic field. And the only difference among them is these are all heavier massed particles. The mass is very, very high. They are bulkier in nature. During your beta emission, that is what your beta is, negative beta. When there, what is happening is your proton is undergoing a transformation. Sorry, neutron is undergoing a transformation. Neutron is converting into proton. So there your electron is coming. During this during this beta emission, there will be a tremendous amount of energy that is missing. When you calculate the reactant side and product side, the energy, there is a loss of energy, and thus loss of energy was not found where it is going. And later, this gentleman has identified there are some other particles which are taking them the energy. Those particles are called neutrinos. So neutrinos will be delivered, and the neutrinos will be involved in this beta emission, and those neutrinos are also taking part when energy calculations are coming into pictures. And neutrinos are still exciting subject. People can study this. And these are basically no charged particles. They don't have any charge, and the amount of mass also negligible. And since they don't have charge, they will not exhibit they will not undergo any electromagnetic force. They don't have any coulombic force of attraction kind. It will not operate, and they don't exhibit even strong nuclear forces. They will be weak, so weak forces of attraction. And even the gravitational force also will be exhibited, but gravitational force can be completely ignored. It's almost near zero. So for all our practical purposes, we don't take the gravitational force influence on these neutrinos. Okay, they exhibit only the nuclear weak nuclear forces. Okay, so why if you see neutrinos, they are continuously coming from the sun to here, to throughout any planetary any planet for that matter. Even it will penetrate through the earth, it will penetrate through all the solar systems. That means they don't have the interactional energy. The weak forces are responsible for their arrival. That's the reason even from the sun there are numerous neutrons are continuously moving. even throughout space when we are moving hand, everywhere around the atmosphere, the neutrinos are there. And one interesting thing is these neutrinos are interconvertible. Of course, while amounting the total number of neutrinos, they found out that there is some amount of neutrinos are missing. That neutrino missing is nothing but the interconversion of one among them. Now we discussed certain forces. I told during the proton inside the nucleus, when the quarks are together, I said one term that is called strong nuclear force. And I also said when weak nuclear force, which is operating among the nucleons, which is keeping all the nucleons inside the nucleus together. That is the uniform density is majorly because of the weak nucleus forces. And again, here while talking about neutrinos, also we were talking about weak nuclear forces, and a gravitational force we also named. Actually, what these forces are, there are 4 types of fundamental forces. That is gravitational force, electromagnetic force, strong nuclear force, weak nuclear force. So these are all major forces. And how this force operates. Suppose sun is somewhere, earth is somewhere else, they are far apart. Still we say that the gravity is operating. How this gravity really operates, whether it is by light or by any fundamental particles or exchange. When while discussing nucleus charges, inside the quarks are exchanging gluons. The gluons are keeping them together. The gluons are responsible for 98% of the mass of the proton. Those gluons are the particles of strong nuclear forces. That strong nuclear forces are being operated by the particles. They are exchanging suppose one up and one down quark, they are continuously exchanging these gluons. That is the reason, because of this exchange of these gluons, only the up and down quarks are there in a small volume with high speeds. So these gluons are some kind of particles. So this force is also being operated by the exchange of the particles. And though we assume that the gravitational force is exchanged by a certain kind of particles, gravitons, but till now there is no solid proof to say that the gravitons are existing. Okay, those who are interested in fundamental research, if you isolate gravitons by somehow, then that will be marvelous. And as you know, this gravitational force operates to a long range. You know, this entire universe, that's a planetary system, they operates very, very long distances. And what is the electromagnetic force? What we are seeing from the sun or all the case or Coulombic forces, what we talk, is because of the charged particles. They are the interactions between the charged particles. That force will operate with the photons. So photons are the force carriers. The force will not happen just like that in an imaginary world. Okay, so the photons will come and go. Because of this, through the photons only they are having the attraction or repulsion. So electromagnetic force operates through the force carriers, which are called photons. And these photons are massless. They don't have any mass, negligible mass, and they are obviously they are the chargeless particles which operate through the charged particles. And you know, the electromagnetic force will decrease with the increase in the distance between the charged particles with the r square. Suppose if you increase the distance by 2 times, the attraction or repulsion force will decrease by 4 times, right? So it is highly dependent on the distance between the charged particles. And this electromagnetic force will operate in the infinite distances. You can calculate it from any distance to any distance. Only thing is, as you increase the distance, the force capacity will go down. Okay, so this is a common force. Electromagnetic force is a very common between any 2 charged particles. And now come to the strong nuclear force. Strong nuclear force is very strong, will operate in very, very small particles, that is keeping the quarks together. Okay, so this is a tremendous amount of nuclear force. Because of that only you are able to keep the particles which are moving with almost the speed of the light together in very tiny volume of the proton. So they are extraordinarily high strong forces and strong nuclear forces. They will operate in very short distance. If you increase from one proton to other proton, then it will not operate. There will not be any strong nuclear force at all. So if you just go within angstrom range also, it will not operate. There it will be operate, the weak nuclear force will operate. That weak nuclear force will operate by two types of particles. Again, the W and Z bosons, where the W is having both kind, positive and negative, and Z bosons are not having any charge for neutron. And again, the research says that the gluons, which are keeping the quarks together, are of 8 types. This gluon force particles are 8 types in nature. Among all 8, 2 of them are very common, 2 of them are very strong, and still further research is going on. And now I wanted to ask, we were talking while discussing about electron energy and other things. You see, electron is having very, very small mass, 0.0005 giga electron volts of mass, whereas top quark, one of the quarks, is having 172 giga electron volts of mass. So by seeing this heavy mass, you may think that the top quark may be of very bigger in size compared to the electron, but that is not so. Both top quark and electron are having almost same size. Sizes are same, but the masses are tremendously different. And what is making them to be so different from one another with respect to the masses? That is, that can be understood only by the interactional force, right? You might have heard, okay, that we will see among all these forces, which one will be the stronger? The strongest is the strong nuclear forces, which will operate very short distances, and most weaker is gravitational force, and little weaker is weak nuclear force, and commonly is electromagnetic force. And how strong this nuclear force is, just to have a feel, which one is higher? I said strong nuclear force is very strong, but how strong? How much strong it is different? Just to have a feel, I have one calculation here. Proton to proton I have done. So assume that the distance between proton to proton is 1 angstrom, 10 to the power of minus 10 meters, and you calculate the gravitational interaction. As being physics students, you may be knowing how to calculate the force of through the gravitation. And if you calculate substitute the mass of the protons, and you get this 1.8 into 10 to the power of minus 44 newtons. So the same proton, you calculate what is the electromagnetic force that is operating. If you calculate electromagnetic interaction between the two charged particles, you know how to calculate. The value is 2.3 into 10 to the power of minus 8 newtons. See how strong this electromagnetic interaction when compared with your gravitational interaction. 10 to the power of minus 8 is much, much higher compared to the 10 to the power of minus 44. It is nearly 10 to the power of minus 30 times. That means the gravitational interaction is very, very small. Now assume that strong nuclear force is 1 unit. So how far they will be small? How small each other forces are? Suppose if the strong nuclear force is 1, the electromagnetic force will be just 100 part of it. That means 10 to the power of minus 2 of it. Weak nuclear force is 10 to the power of minus 6. It's a million times smaller than the strong nuclear force. Okay, and the gravitational force is still much, 10 to the power of minus 40. Means after 10 you put 40 zeros. That much amount of smaller unit it is. So strong nuclear force is 10 to the power of 40 times stronger than the gravitational force. Okay. Why this is happening? Why the particles are gaining mass? What is the basic reason behind the huge mass difference between your top quark and electron? For say, you might have heard, we all are gaining the mass because of the interaction with one energy field. Here is a Peter Higgs who assumed or who proposed that there is a energy field that is operating this entire universe. according to his hypothesis or his proposal, this total universe is filled up with an energy field, and all other particles which are there inside this field are interacting with that field. If you interact more, then more mass will be there. If you interact less with that field, the mass will be less. So how this interaction will be done with that energy field and between this matter is by through Higgs particles. So there are the Higgs particles. When he discovered in 2012, when he was awarded a Nobel Prize, that particles were having a crazy name, God's particle, because entire universe is in energy field, and all masses are just responsible because of the interaction of your matter with your energy field, that is Higgs field. So they were thought to be God's particles. I have one peculiar example. You take one fish. That fish in the ocean will move with it will swim with a speed of 110 kilometers per hour. It's almost all express train. So it will go with such a high speed. But when we try to swim, we cannot move even in meters. Why? It is like here, the fish will interact with this water very less. Whereas this man or human being, we interact more with the water. When we are interacting more with the water, we will be gaining more mass. So we are becoming bulkier. But when this fish simply moves with the least interactions, therefore it will gain less mass. It's an analogy I am giving. It's not exactly. So if you assume that the field, Higgs field or the energy field is like water, your interaction with water is through Higgs particles, and that is responsible for the masses. So if you are interacting more with this field, you will gain more mass. If you are not interacting, you will not have any mass. Okay. So if this medium, this water, this swimming pool, if it is the Higgs field, each and every molecule of water, that H2O, is like Higgs particle. That Higgs particles is giving you the mass. So the mass is converting into energy, energy is converting to mass only in the Higgs field through the Higgs particles. Okay. So higher the interaction with Higgs fields, heavier will be the particle. Interaction of the interaction with this field only is responsible, and mass is just the consequence of this interaction. So why mass is coming, where higher and lower mass is coming, is because the electron is interacting this Higgs field very, very less compared with your top quark. Top quark is interacting more with this Higgs field. That's why the top quark is gaining so much amount of mass. That's why if you interact less with the people, your mind will be least burdened. Your mass will be less. Right? You can take in that way too. If you are moving on your own, if you are not least in the lower interactions, you will be free and your mind will be less burdened. Right? So heavier will be the higher the interactions, heavier will be your mass. To have a field, this is the atom, the total atom, and inside this atom, at the center you have the nucleus. Inside the nucleus you have nucleons, and inside the nucleons you have the quarks. Okay, these quarks are the fundamental particles, and since the neutrons and protons are just made up of two quarks, I have given up and down quarks, and these up and down quarks are together because of the interactions using gluons. Okay, gluons are the major particles which are keeping them together. Okay, so those are other particles, and this is the smaller sizes. So you can compare with the sizes how big they are, and then from one proton to another proton or one neutron to another neutron, neutron-proton interactions, these will be interacted with the weak nuclear forces, and within the proton, the gluons are force carrying particles. They are keeping together, and outside the nucleons, inside the nucleus, the nucleons are interacting with your weak nuclear forces. So this is what the total nucleus. And outside this nucleus, you have electron. This electron is a charged particle. As a whole, this nucleus is also having charge. So this interaction between this charge and this charge is again with your electromagnetic force of attraction. during your electron emission, electron gathering or excitation, when the photons are incident, the force is operated using the photons. So altogether, we have these many quarks, which are the building blocks, and leptons, which are outside the nucleus, and these are the force carrying particles. So up, charming, top, down, strange, bottom quarks, electron, muon, tau, and all these are all leptons, and each lepton is having corresponding neutrinos. So these three neutrinos are again fundamental particles, and all these interactions will be done with your photon, that is electromagnetic interaction, and your gluon, strong nucleus force, Z and W kind of bosons, which are weak nuclear forces, and all these are influenced by your Higgs field, that is H, your Higgs particle. So these particles all together are fundamental particles which are operating now. And again I am saying these are fundamental particles as on date. Like Dalton, who thought atom itself is a fundamental particle, now we have seen hundreds and thousands of subatomic particles. Later, this quark may be having some other, we may prove that the quark is a composite material of something else. But as on date, whatever information we have, today's up to the today's knowledge, these are the most fundamental particles, and this particle model is called standard model of physics. So this is what my talk. And now, before concluding my talk, I just wanted to pose some questions, some areas where I will be excited towards the physics. Though I am not a physics student or physics scholar, I was excited all the time to see some certain aspects in the physics. That is, we know that universe is continuously expanding. And what when it is expanding, where is the exact end? What is the edge of that universe if it is expanding? And how fast that it is expanding? Of course, the research is going on how fast the universe is expanding and why it is expanding through the galaxies. All the time I feel it is excited. And why I'm sharing this is just to give you the some of the areas. If even if you are interested, you can pursue your research career, or you can do your doctoral work, or you can study this. So those are the certain things which I was excited. I'm just sharing. What is dark matter, dark energy? You may be knowing dark energy and dark matter, and whatever research you do with respect to this dark matter and dark energy, still even today I feel excited to know more about that. And moreover, while talking about the atomic structure, I told that inside the nucleus you have the nucleons, and a large amount of the space is free. There is empty space. And same as the case with respect to the universe. In this entire universe, the majority of the space is empty. There is nothing. One planet to the other planet. Planets are somewhere far apart. In between the planets, the majority of the space is empty. And how this time varies with respect when you are moving in the space, how this time varies. The space and time relationship, relativistic effects are always exciting and interesting to know. And you all know that E is equal to mc square, but is it true under all conditions? If I go with the speed of light, when I'm traveling with the speed of light, when I'm moving inside one space to other space, suppose one galaxy to other galaxy, if something object is moving, when that time also E is equal to mc square is valid? Is not. There is something correction factor gamma. So to know about that, how mass is changing, that is another exciting field. And the very concept of mass itself, what exactly the mass, not the weight, but what exactly mass is, what are the various attributions you can arrive, is still exciting, though we know something, but still all the time it will be interesting to know. How this gravitational force, I told the gravitational force is definitely no doubt, there is no doubt the gravitational force is existing, but how to isolate that gravitational particles, whether you can isolate them or whether you can artificially produce using your accelerators or so, is again another interesting topic. And neutrinos, this is still another exciting area of research for the fundamental particle side. Neutrinos are there everywhere and they carry lot of information. Why I am saying lot of information is These neutrinos are having least interactions with any other particles. Therefore, they can travel not from Earth to Moon or Sun to Earth, but they can travel from one galaxy to the other galaxy. Now, if you isolate if you study the neutrinos nature, they carry the information of one galaxy to the other galaxies. No, so when they are having such a huge information, it is exciting to isolate them and get the information from them, because they are traveling through all the systems, through the inside, or even right from the core of the Earth also they are traveling. So they are the basic charge carriers of the entire universe. Now, if you are able to catch them and get the information, then that will give a lot of excitement and full understanding. Those who are interested in doing, I'll recommend them to go for the neutrinos. And even in India, there is one neutron incubation organization that is coming. You can apply there also. That is a DAE, Department of Atomic Energy, is part of that also. And now I already told what is the space and how to measure it, what happens if the space is not there. And this is what I am talking about. India-based neutrino observatory, which is coming. You take part and develop one detector. Since they don't have any interaction, they don't interact with anything, then how to detect them, how to interact them, how to get their information. So those things will be exciting. You can develop any field there. And one more exciting topic is, what are these black holes? What really happening with respect to them? That is also another exciting area you can concentrate. And now, if you really see, we were talking about subatomic particles inside the nucleus, and now talking about the galaxies. Is there any single law which is governing this entire universe at the galaxy levels as well as at the subatomic levels? I think you can see, you can understand also. You are familiar with the solar model of your atom. When we are talking about atom, we compare with the solar system. That means this atomic structure and galaxy structures are same, one and same. You can think, if it is same at macro and micro levels, then that will be very good. Try to derive one equation which will which will be useful for this massive as well as subatomic particle levels. Okay. And when this particles which are coming from them, how to catch them and how to detect them is also exciting area. People say that we cannot move faster than light. Why we should not go? What is making it? What will happen if I go faster than light? And how to go? These are all something exciting. I don't know the answers, and you can pursue the research on those areas in your future. Isolating the subatomic particles, any particle for that matter, is exciting. Those who want to know more about these fundamental particles, I refer them to go to read this book. That is Particle Hunters. Very small book. You can read or you can download. If you don't have also, I'll share. I'll send it to you also, soft copy. A very good book. Those who are interested, if you have any doubts and if you further clarifications, all the things can be addressed in this book. I'll share them. And this is also another good book. And for excitement, latest research you want to know, please go through these sites. Please visit once at least. If you are a physics student, definitely you have to visit these sites. You will find a lot more exciting concepts that you can learn here. And with this, I my talk came to the end. I thank my section head, my division head, and my group directors for permitting me to come here. Today there is some strike in the department. I must go. If I'm not going, they think that I'm in the part of the strike. So I have to go to the office now. And if you have any more doubts and clarifications, please send me the mail. These are my mail IDs. You can write jammuravi@igcar.gov.in and Dr. jammuravi@gmail.com. So I love to interact with the students, not to teach what I know, the most interesting thing is the doubts that they ask will be very much giving me insight of your doubts. If you don't have time, or if I don't have time, you please send your questions. I'll try in my free time to answer you. Please don't leave, whether it is silly question or big question, whatever question it is, you can ask, you can pose the questions, or you can take my number from your Ravi Kumar sir. I will be available even over phone also. So with this, I thank once again for SR&BGNR Government College for giving me an opportunity to interact, to deliver something which I know with respect to the fundamental particles. Thank you, one and all. Over to you, sir.
Thank you, sir.
Thank you very much, sir. Really great session we have listened. Very much knowledge and latest knowledge we have listened from you. Like that fundamental particles, say proton. When we are talking about the proton, such is the composition of three quarks. Having only 2% of mass inside the proton, but the rest of the mass, 98%, is filled with gluons. Then my basic doubt is why we are not calling as a proton made up of gluons instead of these three quarks. Okay, sir. Later we discuss. I will interact with you in mail or other mode. Sir, really.
You can call me, sir. You can call me. We will talk. Basically, they are the basic particles only. They are the fundamental particles only. Gluons and quarks, they are the part of the fundamental particles, and proton is no longer a fundamental particle now.
Yes,
so it is already done. And if you see the person who was discovered this, he was hesitated to publish the paper because people may not accept. What he has done is he found the masses. He has isolated, somehow he got the masses of quarks, and when he amounted that it is only for 2%, remaining 98% is missing. To publish that paper, he was hesitated for 2 years. He could not publish. He was afraid, and that paper was not accepted because it was wrong. Something they were they thought the research is wrong. But later on, now it's published, and now protons and neutrons are no longer fundamental particles.
Sir. Thank you, sir. Thank you. I will interact with you through phone or mobile or mail. So thank you very much. And
sir, one more, my small request. You please collect the questions from the students. I want to see the questions and their doubts. I will be very happy to answer them. Any one of you or Ravi Kumar sir can take the questions, and we will have the discussion.
Sure, sir. Sir.
And one more point also, sir, that conference also, INCAS, one association is there. If you want, if your college wants to organize any workshop, we will be readily available. We will come there with our own cost.
Sir, thank you, sir. Thank you. A little submission from our side, sir. If we want, with our students, if we want to come and visit your center, please make some possibilities to us, sir, if possible.
So, if it is possible, industrial tour is possible. For all the students who are having 18 years and above age are allowed. There is a formal this one will be there. I'll send the details. You can have an industrial visit to our site. You can see the nuclear reactors and other places. I will arrange. I'll inform. You can.
Thank you very much, sir. Thank you. Thank you very much. Visit to us. Sir, now I'm requesting Ravinder Reddy sir, our colleague and also assistant professor, to give vote of thanks regarding the webinar. Thank you, sir.
Can I leave, sir, now or?
Just a moment, sir. Just 2 minutes. 2 minutes format.
Okay, sir. Okay, sir.
Good afternoon, all. On behalf of our SR&BGNR Government and Arts and Science Autonomous College, it is privileged to propose a vote of thanks to everyone, those who have directly and indirectly contributed to this international webinar, recent trends in solar power technologies and elementary particles. And my special thanks to our chief guest and Honorable Commissioner of Collegiate and Technical Education, Sri Naveen Mittal sir, for encouraging us to organize useful events. And we are all very much thankful to Dr. Balabhaskar sir, AGO, for his motivation and support to conducting this webinar. Thank you, sir, for your encouragement. And my heartfelt thanks to Dr. Rajendra Singh sir, RJD FAC, for his kind blessings. Now, I would like to thank our distinguished speaker, Dr. Prabhakara Wobli, Senior Research Fellow, London, South Bank University, UK, for making excellent presentation and making this seminar interesting and meaningful. My sincere thanks to Dr. Jammu Ravi, Scientist IZCAR Kalpakam, for sharing his deep knowledge in the field of elementary particles. Thank you, sir, for information of workshops and project works regarding students from your institution. Sir, I hope our students could avail this opportunity. Thank you, sir, for your excitement towards thought-provoking questions. I would like to thank Dr. Shiva Srinivas, former research associate IZCAR Kalpakam, for giving a reference of Dr. Jammu Ravi sir. I would like to thank to B. Suresh sir, a scientist ARCA Hyderabad, for extending his support in smooth conducting of this webinar. We thank our principal sir, KSS Ratna Prasad sir, for his constant support for conducting this webinar. This conducting of webinar would have been impossible without you, sir. Thank you for your encouragement, sir. We sincerely thank Srimati Anjani ma'am, IQAC coordinator, for supporting us for smooth conducting of this international webinar. My special thanks to Sri T. Jeevan Kumar sir, HOD of Physics of SR&BGNR, for his dedication and enthusiasm to success the international webinar. My vote of thanks would be incomplete without expressing my gratitude for organizing committee members, Sri T. Prabhakar Rao, P. Anita ma'am, M. Lakshmi ma'am, and N. Srinivas Rao, and B. Ravi Kumar sir, and B. Venkateswara Rao sir, who have been working hard to have made this program very successful. And finally, we thank all participants for their overwhelming response to join this program, who successfully completed this program. Thank you, one and all. Thank you.
Thank you all participants, and we are closing this session.
Thank you, sir.
Thank you, sir.
Thank you very much. Dear students, very good.
Thank you very much, sir.
Thank you very much, sir.
Okay.
Thank you, sir.
Good, you have to need